So basically, that feed is going into here, which is Blackmagic monitor, also recorder, and then this HDMI out is going into here. Okay. So this sees that, and then yeah. And so you can check the levels there. You can check them here, and then this should go up and down as well. And it should do it both feeds because this is getting that audio. Yep. So that means we're good to go.
Okay, thank you.
This is Marcus. And I'm gonna lead him to it because he is gonna be so much better at this than I am. I just jiggle cables and hope it works.
Well, it's what we all do. Pretending that we do it for with a good knowledge. Here it is. Oh, I can use HDMI. Yeah, I should have.
We haven't put that.
Let's say VG. Yeah, this is.
Oh, we have a HDMI.
Yeah, yeah, we okay.
Oh, is this? Oh, it's displayed.
Is a VGA? Yeah, yeah, for this point.
Okay. And then plug the USB in for power.
Okay.
Yep.
What was the display port? Is that the other one that's funny, like a more
So
square
yeah.
one?
So that's the Apple port. Apple designed
Did you hear what I called it?
Which-
The funky,
Oh, the-
shorter, square one?
Yes.
See?
There you go.
That's how techy I am.
Do you happen to have
Yes, power
power?
right here.
Oh, perfect.
So,
Do you have a copy of the
program?
program?
I don't.
Let me bring it in.
So if you could go through one or two slides and just make sure
Yeah.
that everything looks good.
Yeah.
Wherever. And it looks like you are. This is a 16 by 9, but it looks like the
Oh,
screen
yeah.
is displaying 4 by 3.
Mhm.
So let me check the resolution settings that you're
Mhm.
sending the.
Absolutely. Yeah, I can play with it.
So yeah, that's.
duplicate this price.
I just want to see if this will have any effect on it. Perfect. Okay. All right.
Thank you.
So there's. Oh, perfect. Yeah. So yeah. All right. That's good. Put my laptop on that. So the thing with the board is that, so these are sort of all the outputs.
Mhm.
So this is sub 1-2, which is this. So these are the front speakers.
Okay.
So right now we're not sending the signal to the front speakers, but if we wanted to, we could. Sub 3-4.
Do you usually send the signal to the front speakers?
No, only when we're like screening a movie.
Okay.
Sub 3-4, those are the monitors in here.
Okay.
So if I press this button, so it raises the button, we're now muting in here. Can't hear anything in here, but it is going out there. And if I press main left right, that's these. So these are the main outs that go to the speakers, the
Okay.
overhead speakers. So if we
empty somewhere? Oh, I need that.
Is it DisplayPort?
Yes.
Okay, I'm gonna have to get you a VGA.
Oh, I have a VGA.
Oh, wonderful.
I have a direct VGA. I have VGA and DisplayPort.
Oh, excellent.
Nobody has VGAs anymore, so. Well, just wait a second.
Yeah, I like VGAs because they work.
They do work like all the time. Okay.
It is cutting off, but
Oh,
we will auto adjust when it's your turn to speak.
and I just real.
You'll be on input.
I'll be on input 1. Okay. Yes.
Go here. Put like this.
Don't look at me, look over my shoulder.
Okay. Jeez. We're good? Okay, I would like to welcome you all to the 2019 Glen T. Seaborg Symposium. I'm very pleased that Paul Alvasados has joined us. 3 years ago, I was tasked by the chair of this department, at the time Kathy Clark, to find the top person in materials and chemistry and nanotechnology. And we quickly decided that the best person is Paul Alvasados. And so it's with that I welcome Paul. Just to tell you how distinguished he is, he's come up through the ranks, and he's actually the executive vice chancellor and provost at our sister school, the California school to the north, Berkeley. Yes. When we looked at who we should invite to represent all the other aspects of nanotechnology, everybody we contacted immediately agreed to come, and so we have a really exciting program for you this afternoon from people from around the world. We're going to hear from Dimitri Talapan from the University of Chicago, Sarah Tolbert from UCLA, Munji Buwendi is coming from MIT, Yuri Bannon came all the way from the Hebrew University in Jerusalem, and then we will get to hear from Paul Alvasados. So I just want to say one thing about the Seaborg. We've been doing this for 32 years. I've had the privilege, I joined UCLA the first year of the Seaborg Symposium. And besides this symposium, which goes to somebody who's truly deserving, in fact, we've had I believe 9 Nobel Prize winners received the Seaborg Award. We also have what I call the Junior Seaborg Award, because Seaborg founded Alpha Chi Sigma, the chemistry fraternity at UCLA. And so in the spring, a professor under the age of 40, in honor of Glenn Seaborg's Nobel Prize at age 39, receives that award. So I was fortunate to receive that award one year, and it was about 7 years later that they named the element after Glenn Seaborg. And at that symposium, Seaborg's son came to me and he said, "Rick, you won the award. Did my father ever give you his pin?" I'm like, "No." He said, "Come with me. Dad, he won the award. You should give him your pin." So I have a Element 106 pin given to me by Glenn Seaborg. All right, let me say a few words about Paul. I've known Paul for many years. When I was a postdoc at Berkeley, I think we first met. He was finishing up his graduate work. We became very good friends. And a few years later, we both did a military mission together for 2 years, the Defense Science Study Group. And so if you want to see some compromising pictures of Paul in military, with the Marine Corps or on aircraft carriers, see me later. Yeah. Yeah, I could have put them up, but it's... Yes, there we go. So it's my special pleasure to start off this symposium, and I spent some time as the associate director of this institute, and Paul is one of the foremost leaders in the world in nanotechnology and in materials chemistry. And with that, I'm gonna call up Professor Yu Wang from Materials Science and Engineering to introduce our first speaker.
It's my great honor today here to introduce our very first speaker for the Seaborg Symposium, which is Professor Dimitri Talvin. He's a Louis Brock Professor in the Department of Chemistry and James Franck Institute at the University of Chicago. He's also a fellow of the Royal Society of Chemistry and the associate editor for the Chemical Science published by the Royal Society of Chemistry. Dimitri was born in USSR and he grew up in Belarus. He received his PhD from the University of Hamburg, Germany in 2002. And after that, he became a postdoc fellow in the Lawrence Berkeley National Laboratory, working at the molecular foundry there for 3 years before he became the faculty member at University of Chicago. He has many exciting research activities in materials chemistry and nanotechnology, which includes the development of novel methods for nanomaterials synthesis and the self-organization of nanoscale units into long-range ordered superlattices, and also the surface chemistry of nanomaterials for device application, among many others. So for his excellent work in this field, he also received a lot of the recognitions and distinguished awards, to name a few. He is the recipient of the 2018 ACS Inorganic Nanoscience Award, the Material Research Society Outstanding Young Investigator Award, the top 100 chemist of the decade based on the citation impact by Thomas Reuters, and also the prestigious David and Lucille Paca Fellowship in Science and Engineering. So without further delay, I'll give the stage back to Dimitri.
Thank you very much. It's a huge honor for me to be here and speak at the symposium in honor of all organizers with whom I worked together for 2 years at the molecular foundry. Okay, thank you. And well, I will, first of all, I want to remind you that Paul by training is physical chemist, and that's why I will talk today about some projects that are more related to physical chemistry than to like inorganic chemistry, that is another part of our activities. And also, I want to give a little bit of history and relate the work to what Paul and others in the field have done. And actually, after working in the field for now close to 20 years, I feel that what you guys have developed is pretty much not more and not less, but the causing of organic macromolecules. So you opened up a whole world of inorganic macromolecules that eventually will have comparable impact at some point as what we now know in from polymers. And that's probably the long-term impact of Paul, Munges, and many other people who contributed to the field. But it takes time. So, and actually, I think this is the very first paper that Paul published as an assistant professor. Oh, second. Okay. So he, when he just started his work, he decided to work on gallium arsenide for a very good reason. Gallium arsenide is the material that where all the excitonic physics has been discovered in quantum wells and other low-dimensional structures. And but I have to, well, nobody can say that Paul has chosen a very easy problem to start with. So it turned out that it's an extremely complex system that kind of opened a whole world of questions and pointed to fundamental limitations of the whole like colloidal methodology that I will try to talk about today. So like, why gallium arsenide? Gallium arsenide is a very handy material when you grow it by chemical vapor deposition, by reacting gallium and arsenic precursors at about 700 Celsius. It works, and works very reliably. It took us some time as a community to come up with colloidal routes. That way we found equivalent gallium precursors, arsenic precursors, like all this makeup after synthesis and purifications. But then we made particles that looked very exciting. They looked like nanocrystals in transmission electron microscopy. They look like single crystalline. You look at X-ray diffraction signatures. Everything is perfect. Time to declare victory. And up until the moment that you bring these samples to the spectroscopy lab, and then you see nothing. There is no excitonic peak. There is no size-dependent redshift of the absorption edge, and pretty much everything that gallium arsenide is known for is not seen here. And if you do time-resolved spectroscopy, you won't see even any sign of photo-induced bleach. So it just doesn't act as a two-level system. So, and actually, another thing, if you look at these materials, you measure Raman spectra of this material and compare it to the Raman spectra of bulk gallium arsenide, you don't see acoustic, even optical modes that are characteristic of gallium arsenide crystal. And some of the most telling data came from EXAFs. So if you compare gallium edge of bulk gallium arsenide and these particles that looked as fine gallium arsenide made by solution-based solution methods, you see that the amplitude of EXAF's signal is very much the same. So you have, on average, each gallium atom is surrounded by each arsenic atom is surrounded by 4 gallium atoms, and on the other hand, if you now look at arsenic edge, and for exactly the same material, you will see that arsenic is undercoordinated. On average, every arsenic is surrounded by 3 to 4 gallium atoms. And that, if you reconcile it, you see that this material is full of point defect vacancies, gallium vacancies. And luckily, it's gallium arsenide, so you can find a lot of old literature coming mostly from Bell Labs. And it says that no matter, guys, how you grow your gallium arsenide, if you do it below 500 degrees Celsius, you will end up with a very, very defective material. And there will be vacancies, there will be anti-sites, and there will be a whole world of point defects that we don't usually think about when we work with ionic compounds like 2,6. At the same time, that same old literature suggests that if you take your bad like defective gallium arsenide and heat it to 500 degrees Celsius, it will kind of recover, self-anneal. And that's what happens. So you can make a film of these particles and anneal them, and they recover a Raman spectrum of gallium arsenide from what it was before to. And you start seeing, like, they're still quite defective, but you see size-dependent bleach, and you recover properties of gallium arsenide of direct gap semiconductor. Now, but that brings the whole question. So, of course, after you anneal the film at 500 degrees Celsius, you cannot redissolve it. So, can we do solution chemistry at temperatures comparable to what people do for CVD, and MBE and other great techniques? And in solution, we are bound by chemical thermal stability and chemical stability of ligands, solvents, particles, and all other components. And we have a pretty hard ceiling around 400 degrees Celsius, because at this temperature, carbon bonds start falling apart. At the same time, if you go to textbook, solid-state chemistry textbooks, you will find a whole world of compounds that require high temperature to even form and be stable, like nitrites, carbides, gallium arsenide. So we started thinking along these lines, what can we do to expand the parameter space, the boundary conditions that solution chemistry, relevant to solution chemistry, and we found that came with an idea to explore molten salts, inorganic salts, as solvents. And just can we do solution chemistry scalable and take all advantages of traditional solution chemistry, like scalability, like precision, size and shape control, but do it without this hard ceiling, temperature ceiling. And it may sound like a totally crazy thing when we think about molten salts, but not really. If we look at the eutectic mixture of aluminum chloride, sodium chloride, potassium chloride, it melts around 97 degrees Celsius. So in principle, you can interface it with toluene or many other solvents. So does not require you to rethink everything that you knew before. And we've been kind of lucky to find that in molten, you can make colloids in molten salts. And that's that was missing. Of course, people in the past did flux chemistry in molten salts, did a lot of solid-state chemistry in molten salts. But I'm not aware of any work on colloidal chemistry and colloidal states in molten salts. And that puzzled me from the beginning, because how comes molten salts have been around for a century, at least. Small particles have been around for the same long. Why people did not see this effect? And the only explanation I can come up with is that actually the formation of colloids in molten salt goes just orthogonal to our common sense and intuition of what you need for colloid. Because if we talk about colloidal dispersions in polarizable media, in polar solvents, we typically rely on DLVO, or Diragen-Landau-Fervey-Overbeck, or extended versions of this theory that kind of explains what can form stable colloid, what cannot form stable colloid. And the idea is that to form a stable colloid, you should have net repulsive force between nanoparticles, or between particles, or droplets, or whatever. And you need to equate within DLVO van der Waals attraction, which will be always attractive unless you do index matching, and you cannot do index matching for many materials in molten salts, and electrostatic double layer repulsion. And everything looks fine up until you look into this electrostatic double layer repulsion, that electric field is screened in the polarizable medium at the distances defined by the Debye screening lens. And since you have a very highly concentrated, very high ion concentration, there is no way how you can make double layer repulsion anyway comparable to the van der Waals attraction. So these materials should not exist, should not form, well, at least cannot be explained by DLVO, but at the same time, X-ray scattering data and many other techniques suggest that it works. So, and with that idea in mind, we tried to better understand what happens at the interface of a crystal and a molten salt. And the Debye lens is pretty much comparable to the interatomic distance. But in a highly concentrated molten salts, you see development of a charge density wave that comes through recharging of surfaces, and that creates a whole new regime. That if we plot like the bilance normalized to interatomic distances or lattice distance and actual screening lengths at low or at dilute solutions, at low ionic strengths, we have traditional in the bihucular regime and traditional DLVO colloids. And here we switch to a new regime, or at least that's what computational work suggested. And we needed to, next step, we wanted to test it. Like, okay, theoretical proposal is always good, but we wanted to see this charge density wave of recharging colloids that propagates, if this calculation were anywhere close to be correct, by at least an order of magnitude beyond the Debye length.
Sorry, what's the y-axis?
It's a screening length. It's a decay. Or
That you have x-axis is the reciprocal.
yeah, it's a reciprocal screening length, and this is again same reciprocal screening length. So here we have Debye length, and here we have experiment or like the length that we get in simulation. And and then we did so-called double differential pair distribution function analysis using hard X-rays at Argonne National Lab and extracted new correlations developed in the molten salt in presence of nanocrystal. It's a rather involved experiment, and we heavily relied on expertise of beam scientists there. But the idea is that you measure pair distribution function, you measure PDF of colloidal solution, and then you subtract PDF of particles and PDF of pure solvents with correct weighting, and extract what's new, what happens, what new correlations are developing in solution due to surfaces. And we found that pretty universally, as soon as we put particles in molten salts, we develop these waves that match pretty well to what we saw computationally. So probably, jury is still out. We still don't have a fully self-consistent picture of what leads to colloidal stability. But we see these long-range interactions, like transient ordering, developed in molten salts due to nanocrystals when we have a colloidal suspension, colloidal dispersion. Now, but moving back from fundamental aspects to more pragmatic aspects, I think we have now a good opportunity to redesign the parameter space for solution synthesis. So we can remove this physical boundary condition related to boiling and thermal decomposition of solvents. In terms of chemical boundary conditions, like we are always kind of limited by nucleophilicity of reagents that we can use, and oxophilicity. And a good analysis, a good example could be sulfur versus phosphorus. Like when we put sulfide, it will be fine. Chloride will be fine in most solvents. P3- will be extremely nucleophilic. It will attack everything that can find and attack. Same story with oxophilicity. Like cadmium is not oxophilic. We can make cadmium sulfide selenide nanocrystals almost in air. For gallium salts, if we have any precursor, any molecule containing oxygen in any bound state, we will end up with gallium oxide. And so in molten salts, we can eliminate this. So for example, we can take this colloidal gallium arsenide, put them in molten salt. In this case, we used inert bromide eutectics. And we can introduce gallium iodide, and we just infill we infill vacancies and recover gallium H. So now it looks like bulk gallium arsenide, and we start seeing development of size-dependent fundamental absorption H. We see excitonic peaks. Of course, a lot of work should be done to further polish this material, but actually it shows like a first step, and the reason, and we also found, I just kind of jumped on other opportunities, and one of the most interesting opportunity here, well, one of the reasons why we kind of stopped working on gallium arsenide, because it contains arsenic that is potentially toxic, and we kind of didn't see a big goal at the end, except like making this material. But we found that we can make compounds that our community tried to make for like 30 years with very limited success. So we can make indium gallium arsenide, indium gallium phosphide, actually building on Paul's work on ion exchange, but doing it now in molten salts at very high, like 450 degrees Celsius. And we can make very emissive, very bright and narrow indium gallium phosphide. Why indium gallium phosphide is a potentially important material? Because right now, all the industry, display industry, is run on indium phosphide. Indium phosphide is less thermodynamically stable if you just compare free energies of formations in indium gallium phosphide. And as a result, it does not decompose. Another problem that we have in case of 3,5 traditional technology like indium phosphide based, we only can make core shell structures with 3,5 core and 2,6 shell. And that means that we need to have very sharp interface. And this interface has been at least, this interface is typically associated as a troublemaker for Auger rates and other detrimental effects. And while in 2,6 materials and in potentially now in 3,5 materials, we can make 3,5, 3,5 or 2,6, 2,6 alloyed shells and pretty much design the confinement potential. And in such structures, you can make materials that are just act much better at high temperatures. They don't lose emission in colloidal solutions. So it's potentially a path forward. By any means, I don't want to say that it will replace traditional methods, but it may bring us one step closer to what high-end methods like MBE and CVD can deliver, and now we can do it in solution. But a lot of work to be done. Now let me switch gears and talk a little bit about a different project and something that will also can be traced to Paul's activity. And in many cases, when we design these quantum dots or other nanomaterials, we keep in mind something like this path, where this is our input parameter. And at the end, we want to have a device, either solar cell or LED or something else. And that vision has been present from day one. And probably and over the years, it has developed into a vision like that nanomaterials, colloidal nanoparticles, can be a great universal platform that can be used for transistors, for light-emitting devices, for photoresistors, for photovoltaics. They are non-epitaxial. They can be integrated with CMOS readout circuitry, and they can be integrated into flexible, stretchable devices. So it's a huge kind of parameter space that can be serviced using solution processed and printable devices using quantum dots. And I'm not an expert in science history, but probably that was the first work on quantum dot devices, of high-profile work on quantum dot devices, that pretty much set the stage for quantum dot LEDs. And at that time, it was just showing that, yeah, in principle, these materials work. And that kind of evolved over the years. After 25 years of research, like a couple months ago, I visited my former student who is now leading chemistry development at TCL, and he has shown me like this example, their production or their research. It's research for pilot facilities where they make, like in this case, it was one LED. Here we have 22 million individually addressable LED pixels that provide superior color purity to OLEDs, and well, of course, many technological problems have to be solved, but it looks like a very competitive technology with respect to OLEDs. So there is a long way to, well, this field went, but of course there are many other opportunities and many other types of devices, and they all now relate to the conductivity, to the ability to efficiently inject charge carriers or extract charge carriers from individual quantum dots in the films, in the active layers. And that brings us to a different kind of design, chemical design space. So it's now not about particles themselves or quantum dots, but about the interfaces. And how can we engineer interfaces? How should we understand transport through the interfaces? And this effect is huge, because if you have same types of particles and put is a relatively insulating ligands that we use for synthesis, or like more optimized ligands that are good for electronic conductivity, the difference for the same layer of particles in conductivity or charge carrier mobility will be many, many orders of magnitude. In this case, for gold particles, it was 12 orders of magnitude. So we just, by designing surface ligands, we can bring particles from highly insulating to highly conducting regime. And in the beginning, and all these devices like LEDs and photodetectors and solar cells, they all kind of rely on efficient charge, ability to shovel charge in and out of quantum dots. In the weak coupling regime, when you have relatively thick or like organic ligands, everything can be nicely described by hopping, where charge carriers like hop downfield from particle to particle. And mathematically, it's described by, or physical picture is very nicely agrees with variable range hopping with Coulomb gap, also called Efrosh-Shklovsky variable range hopping. And that's what happens when you have very, very low conductivity samples. Over the years, chemists started making some progress on making better and better ligands, like some either highly transparent organic ligands or inorganic ligands that enable more efficient charge transport between the dots. And then some interesting transport pictures started emerging. So like in this case, hopping times become in femtosecond regime, like interparticle resistances become a sizable fraction of quantum resistance. And all this kind of manifested to an interesting regime where mobility increases with decreasing temperature. And in molecular electronics, it's known like band-like charge transport. And something interesting and definitely deviating from a classical picture of hopping started emerging, and we need to understand that. And as soon as, and for every material, like when mobility becomes high, like typically higher than 1 centimeter square per volt second, you start seeing development of this band-like region. And it was seen first in cat selenide, and it was seen in indium arsenide. A lot of great work was done by like Sherry Kagan's lab and Matt Law at UC Irvine. So it just something universal is emerging. And at the same time, the physics community, when they started analyzing it, start bringing up the point that, okay, the system has a lot of disorder, and it's just a standard mathematical or physical treatment of transport within mod single electron type. Treatment just does not permit formation of delocalized states and other complex phenomena like bringing particles closer to the conduction, like band conduction as we know it. Same like there were great works showing that in order to form metal, to make quantum dots a true metal at 0 Kelvin, you would need to put like something like 13 electrons per 5 nanometer size particle, something that would not be compatible with quantum dot, like with optoelectronic applications of quantum dots. There was another interesting work from Frank Weiss and Tobias Hondrath suggesting that, okay, even if we epitaxially neck particles, we still, and make a long-range superlattices, we still have mobilities, very low mobilities, and hopping regime. So there is a discrepancy, and these are very credible, great physicists. So there is a discrepancy like between what chemists claim and what physicists claim. And it was not clear, well, there were all kinds of discussions where it comes from. So it's, and the problem is like, with understanding it, is that we have 3 energy scales in the problem, like disorder of site energies, like energy difference between individual particles. Then the exchange coupling energy, the coupling integrals that bring wave functions together and couple them, And also Coulomb charging energy or self-capacitance that also forces system to end up in a Mott insulator regime. So, and well, altogether there was clear discrepancy between experimental data and theoretical analysis, and there was even an article written to be or not to be. So, but so it's well, I think we have good estimates on this on each of these energy scales coming from site disorder, from Coulomb charging energy. One parameter that I think is taken pretty much out from the blue sky is exchange coupling energy. I don't think DFT can give a good estimate on what's going on. So after like years of these debates, we decided to team up, join forces, and try to better understand what's going on in this system. And we approached it from two opposite regions. Like when we talked about we first demonstrated band-like transport. I definitely was naturally an advocate of this. And my colleague, Philippe Giossiane, who is more physicist by training, pretty much approached it from totally opposite, that it's not possible, period. Well, delocalized transport. So we decided to work together. We had a postdoc from my group, a great student from his group, and tried to better understand it. I think it's a good exemplary case when how science should be done. So we picked a system that we both were interested in at that time, and Philippe worked on it for 10 years or so. And it's mercury telluride quantum dots. They are, in the bulk, they're semi-metal. And so it means that you do need quantum confinement to open up any gap. We have pretty good understanding of their electronic structure. And these materials also turned out to be practical for, this is thermal imaging taken with these quantum dots. So they are pretty interesting mid-infrared photodetectors. So, and then we decided to unleash our chemical skills to optimize the surfaces, interfaces, ligands. And we designed an ink that was a soup of 3 or 4 different components, but these are halide, mercury halide, or chloromercurate-based inorganic ligands, and dispersed in DMF. And nothing happened to the particles during ligand exchange. They still show photoluminescence. Particles are amorphous. And we also measured, did very careful studies of temperature-dependent structure factor of the film. And we didn't see any contraction of the interparticle distances, just because there was a very nice work by William Tisdale suggesting that if you have organic ligands, they can contract over temperature separately. So we didn't see this effect here. And and separation between dots was about 3 to 4 angstrom. So just good film, nothing special. And then we made field effect transistors out of it with zero thermal budget. Like everything was processed room temperature, nothing annealing, no annealing, nothing. And then we saw that as we measure transfer curves of transistors. So the idea, what happens is that when you apply a bias between source and drain and gate electrode, you pretty much charge up planar capacitor, and you add additional charges into quantum dots. And all these charges are confined within the first layer of quantum dots defined by Thomas Fermi screening lens. And so we just charge these dots. And this, on the ensemble of dots, we now see like very nice filling of the quantum states. Like S, we put 1 electron in the S state, then we put 2 electrons, we block this layer. Then we put 3 layers on the P's, and we block P layer. And we can even see much more subtle effects, such as, for example, in this sample, we had, we have S state, and we have P state. And then if you compare it to the intraband transition, you can see something that people didn't know before, that in mercury telluride, the intraband transition is split into a manifold of 3 states, and due to spin-orbit coupling. So you just recover. So you see pretty subtle effects that convinced us that when we claim that we put electrons into S level, it's on S level. When we put it on P level, it's on P level. And then we can make devices. And actually, material is amazing. We did all the processing at room temperature in air. So I would never expect that tellurides can be stable, but they are stable because they're narrow gap. And so we can then extract mobility from transconductance. and we know exactly how many electrons are per quantum dot. We can also extract them from conductivity or conductance of the film, and we also know exactly how many electrons we have. And that's what we extract, and we see that, that first of all, what was very exciting, that mobility, without any annealing, with clearly resolved density of electronic states for quantum dots, we can have mobilities on the order of 8 centimeters squared per volt second, which is huge, at least 2 orders of magnitude improvement compared to any previous work where people could resolve quantum states. And also we saw that in order to see this development of a negative temperature coefficient of mobility, there is we need to cross a certain threshold, around somewhere close to 1 centimeter squared per volt second. So only high mobility samples show it, and which actually was an interesting and puzzling observation that we now wanted to understand it. And there are multiple theories or theoretical models how to analyze these effects. Of course, we can use Shklovsky variable range hopping, and we can use Bloch-Boltzmann theory that is more typical for, common way to treat transport in like single crystal semiconductors. There is a good way to identify middle ground based on the Marcos theory, where we just define the donor and acceptor pairs and treat particles as donor-acceptor pairs along the reaction coordinate, and then see how the reorganization energy relates to the coupling integral. And we tried them all, and we found that we found difficulties. So, for example, Marcos theory can nicely capture the overall shape of the curve, but first of all, this relation of we are clearly away from out of weak coupling region. So we are already pushing the boundaries of where this theory can be applied, and we also see a very large discrepancy at low temperatures. Like there is pretty much no, very small activation energy for transport in a system where static disorder is at least about 2 orders of magnitude larger, at least an order of magnitude larger. For Shklovsky, we can capture, if we fit a low temperature regime with variable range hopping, we arrive at the localization length, which defines the coherent region of the wave function to be larger than, significantly larger than individual quantum dot. Okay, so we just take it as a data set. So I think all of these theories models are pushed to the limits. And we want to, and we need some additional ways to think about it. Probably the best quantitative fitting to the data that comes if we treat the material using as a heterogeneous conductor with strongly coupled regions and weakly coupled regions, and we can map it on a resistive, equivalent resistive network, where, like, if we have metallic islands and with hopping between them. But okay, we can extract some information from temperature-dependent transport, but we need other methods. And one of the most useful, powerful techniques for transport studies will be Hall effect. And there is a massive body of literature suggesting that in order to observe Hall effect, you need to have some, the carriers must flow. They cannot hop, because you will not develop Lorentz force you won't have group velocity in the hopping regime. And at least theoretical predictions are that in the delocalized transport, you should have comparable Hall and drift conductivities. In case of hopping regime, it should be very low. And Hall effect should be very low, very small. And we observed amazingly good development of Hall effect, nearly ideal Hall effect down to like 10 Kelvin, and with very comparable Hall and drift mobilities. So again, it's another bit of information. And another system is, another way to look at transport physics is to measure temperature-dependent Seebeck effect. And there are predictions, like for metallic transport, we deal with traditional, well-known transport, Mott formula, where Seebeck coefficient is proportional to temperature. For the hopping regime, there is a predictions from Mott and Davis that it should scale as square root of temperature. If we compare, and if we now compare experiment to these predictions, we can see that our dots show linear temperature dependent of Seebeck coefficient with temperature, which is more typical for metallic diffusion when you have Fermi surface. And again, I think these are kind of different observations, and we did a very meticulous analysis of different experimental observations that now I think a ball is on the side in the court of theoretical community. We need to reconcile all this. But what I want to say for sure is that quantum dots can be good electronic materials while preserving their quantum states. And one way I think that I now think about transport in this high mobility quantum dot solids is that we may have, well, we have multiple evidences that there is some degree of carrier delocalization. We don't have a massive metal insulated transition like mobility edge. And this theory, I think, is too idealistic. And so instead, the system, as soon as we, as usually chemists, improve quantum dots and their coupling between quantum dots, we gradually move along this axis from like improving carrier mobility. And that just leads to gradual transition from a small exciton, or small polaron picture where states are localized on individual dots to larger to medium polaron where dots, like coherent states spread across like small clusters of dots to larger polarons. In extreme case, it will be infinitely large polaron if it is possible. But that's actually a picture that is now emerging in organic electronics, typically single crystals, with very recent theoretical developments in this field. And the most, well, now, but again, I think we need theoretical work to be done properly at this point, and we have very good model system to do it, to validate data, theoretical analysis. So I'm now moving to the most important part of my talk. I'm really privileged to work with a terrific group of students and postdocs, and I also want to thank you for your kind attention, and I want to remind why we are all here. Thank you, Paul, for everything you did for the field. And also, well, it was a great, I think you were a great catch for University of California, given what you have done. But also, I want to remind you about your roots. And thank you.
Really interesting work. So I'm very curious. So can you actually extract voltage out, or like power out of when you do these measurements of current? Because one of the questions has always been, well, maybe you just, and especially with the mercurial, where you're literally of a semi-metal on some level, like, is there just some sort of metallic or percolation pathway that these charge carriers can go through that gives you this sort of almost perfectly conductive system? Or can you actually extract like the voltage differential you would expect from the quantum confined particle?
Absolutely, excellent questions. So first, we would not be able to modulate transport by gate if there were no gap. Second, the detectors that I've been showing, mid-infrared detectors, would work in photovoltaic regime. So they are photovoltaic. So it means that you do have, well, you extract power. That's what you measure to image.
Right. You have to extract some power.
Yeah, you extract power. Yeah. It's not resistive. Also, we measured the detectivity, D star, from these materials, and we saw a expected scaling, like D star scales as square root of mobility. That also implies that you don't close any gaps, and it's a surprisingly well-behaving system.
So with the molten salt work, beautiful. Why is it that you can't nucleate? Sorry, in the molten salt work, why can't you nucleate and grow directly in the molten salt? Why do you have to do that grow at a lower temperature first and then try to recover the, you can't get as good materials in the first instance in the molten salt itself.
Well, we are conservative people probably. My group is full of conservative students. We started from simple things and moving towards more and more wild. So the problem is that, not a problem, like an observation is that it took about 30 years to our community to master balance of nucleation and growth in traditional solvents. And we want to capitalize on this. And yes, we can do some synthetic work in molten salts directly, but controlling size distribution, now it's like forgiven. Of course, like you mix these 5 chemicals and everything works magically, even in hands of freshman undergrad. But it took 20 years at least to find these 5 magic additives. So that's pretty much the story. We start with, we want to capitalize on what we already know and build into new territory. But eventually, there is nothing illegal. Just need to first develop empirical body of knowledge. That and big, I don't know, body of empirical knowledge and failed experiments that we will take advantage of.
Also related to the molten salts, the charge density, weight. That reminds me of ordered water on the surface of proteins, and especially ion chains.
Absolutely. So so that let me repeat the question. So this layering of ions is qualitatively similar to what people saw at the surface, like hydration layers of water at the surface of membrane proteins, on the cellular membranes, and absolutely. So it's we got a lot of inspiration from that work. The reason why, but the underlying physics is very different. So here it's pure electrostatics, and in case of hydration forces, it's mostly like hydrogen bonding and dispersive interactions. But so there is a similarity.
I was really curious about your Hall effect measurements, because in Hall effect measurements, if you don't have band-like transport, the carriers that have to hop end up screening the field, and so you usually underestimate the carrier concentration and overestimate the mobility. And yet you were doing the Hall effect measurements through the regime where you changed from hopping transport to band-like transport, but you got this, almost spot-on agreement with the FET mobilities. I'm just wondering, how does that work?
Well, it's so there are multiple ways how to think about transport in the hopping regime. My probably rather qualitative understanding is that we preserve, if we have a heterogeneous system with metallic islands and with Purk interconnects, at high temperatures, it's electron phonon scattering that is determined by, determine overall transport. But since the conductivity transmission through this inter-island regions exponentially drops with temperature, we still, that's what becomes dominating drift mobility. And in the Hall effect, it's it's like correlated hopes or like correlated moves. Probably it's more sensitive to localized transport inside the islands, and that doesn't change with temperature. That's, again, I don't quote me on this, but that's how I think about it.
That's exactly where I was going, was what's the length scale by which once you have correlated motion, the Hall effect measurement is clean, as opposed to we now have carriers that can't respond to the field and don't give you the right Hall voltage.
Well, in many cases in the hopping regime, when you have microscopic hopping regimes, actually when you develop Hall voltage, carriers will hop against it, it will cancel it. But I think it's a fascinating problem for the physics community, for theory community to tackle.
Well, thank you, Dimitri, for a great talk.
Thank you.
Field service to
Yes, I'm Bill Gelbart, and I'm very pleased to be able to introduce our next speaker, Sarah Tolbert, a colleague for over 20 years and an immediate next-door neighbor in Young Hall. We literally bump into each other many times a day, and it's almost always a good thing.
I think that was a compliment.
I've been a fan of Sarah's from the time she came, and even before. Her PhD work with Paul involves some real experimental tour de forces, and in particular, an experiment I still think of vividly. They weren't only the first to look at solid-solid phase transitions in nanocrystals, but to do so under very high pressures, doing the experiment in a diamond anvil cell. She did her postdoctoral work at UCSB with Galen Stuckey. It's when she began working in messy materials chemistry solution. And she's been doing everything since, namely covering the full spectrum of materials chemistry science. It's hard to put any label on Sarah, something I admire very much. The only clear label that applies is a great scientist. She's worked on super hard, ultra incompressible materials and characterized them, on multiferroics, materials that are at the same time ferromagnetic, ferroelectric, ferroelastic, on semiconducting polymers, especially in the context of composite mesoporous materials, photovoltaic, light harvesting, solar cells. And she's also been one of the most important leaders of interdisciplinary research on campus and more broadly. She's the director of the DOE Energy Frontiers Research Center, focused on rechargeable batteries. It's a multi-PI, multi-campus effort. She's led our most successful outreach programs on campus. She's been the director for years of the CNSI outreach program in nanoscience, bringing high school students here for the summer, training over these years hundreds of high school teachers, helping them bring back cutting-edge nanoscience demonstrations and experiments to their classrooms. She almost single-handedly spearheaded the start of undergraduate materials chemistry majors and our graduate program. We have a PhD specialization in the department now, largely thanks to her, in materials chemistry. She's also one of our very best teachers and best mentors of graduate students. So she is a triple, quadruple threat, and that's why I am such a fan of hers. So glad to have her as a colleague. From the general title, I'm not clear what she'll be talking about, but I am sure that it will be something very interesting and exciting.
Thank you, Bill. I truly appreciate your overly kind words. And I also, it is such a pleasure to be able to be here today and to honor Paul for this symposium. And I have to tell you, Rick already mentioned this, but I've organized a lot of symposiums through the last few decades, and never before have we invited such an illustrious set of guests and had every single one of them say yes to our invitation. And I think that that is a testament to the respect that the community has for Paul and our joy at having an opportunity to celebrate this award with you. So thank you, and thank you to all the speakers who so kindly said yes without making us nag you, which is almost unheard of in this day and age.
We just had to nag them for titles.
Well, that's not my problem. I didn't do that part. Yeah, administration, you probably get nagged for. Okay. We are still trying to make it the right size. That's not the right size. That's 3/4 of the right size. That's definitely not the right size. No, that's also not the right size because the edge is cut off, and some of the slides don't have edges, and so then the data is cut off.
Can we transition to that laptop?
Is it a PC or a Mac? I suppose we could, if that would make your life easier. I just have to find the USB stick that I put it on, which, some slides are will be cut off. So, can we just do it with the other port with HDMI? Would that fix it?
Is there any, where's the HDMI port? We can try.
Because that would be easier. Okay. We just did it with the HDMI.
I need the VGA HDMI then.
Oh, VGA HDMI?
Yeah.
That I don't have.
Okay, then let's use this guy.
Okay. I don't trust anybody else's computer, but we will have to hope that that's also slightly cut off. Do you have more USBs?
Yes, there's a USB over there.
No, there's not.
Oh, sorry. I don't, for some reason, it doesn't want to display your borders. This is pretty perplexing.
Okay. Wait. This is not. This is not right because this is not. Oh, wait. This is not the right presentation, I think. Yeah, you just opened the wrong presentation. So let's not do that. Let's open. Wait, you're ruining my animation. Okay. Okay. Are we functional? Yes. All right. Sorry for that. Let us begin. Okay, so when I was approached about giving a talk, I invited people. I said, Sarah, would you like to give a talk? Yes, thank you very much. I'd be pleased. And so the question was, what topic should I talk about at a symposium honoring Paul? And there's really a lot of different things in my group, and everyone asks me what I'm the most excited about, and the answer is usually everything. We wouldn't be doing it if we weren't excited about it. But in thinking about a symposium that is in honor of Paul, I thought, what is a project that has its fundamental roots in science from Paul's group? And so the title I gave was, as Bill said, very generic, From Phase Transitions to New Functionality in Nanostructured Materials. And this is not the title that I generally give when I am talking about this topic. Generally, I give a topic that is something more like this: fast charging batteries from solution processed nanostructured materials. And that is indeed what I'm going to talk to you about today, how we can use nanoscale materials to create batteries that can charge in potentially just a few seconds or minutes rather than hours. But really, what I could have labeled this talk as is how an esoteric thesis could lead to something as practical as a fast-charging battery. Because really, the origins of the story that I'm going to tell you today are old. The origins of the story from today really find their roots in my PhD thesis with Paul. And when I joined Paul's group, I wanted to do something cool and fundamental, and applied was a dirty word back there. We didn't say applied because that wasn't true science. And so we picked a project that was truly fundamental in nature, and we really never dreamed it would have any applications. And the idea was to ask, now that we could for the first time make nanocrystals, small-sized crystallites, could we ask how fundamental processes like a first-order solid-solid phase transition would change with size? And indeed, we used high-pressure cells and things that would never be practical for any kind of device. But we came up with some very important conclusions, which is that if you ask how a phase transition in a nanocrystal from one crystal structure to another changes with size, there are two fundamental changes. And the first of those is thermodynamic in origin. In a nanocrystal, the surface comprises a very large fraction of the atoms, and so the surface energy is a significant fraction of the total energy of the system. And when you undergo a phase transition, you can change that surface area and those surface energies. And so that surface term can add a big component that modifies the overall phase transition energy. But in addition to that, you have to kinetically get from here to here. And that usually occurs by a process called nucleation and growth, where you nucleate a critical nuclei of the new crystal structure, and that critical nuclei propagates across the material. And we found that that nucleation and growth process was also made much more difficult in finite size, and so you modified also the kinetics of phase transitions. This is where I left that project. Paul's group went on to do a lot of really exciting work, again, looking at many more of the details of phase transitions in nanocrystals. But as we go back to the main topic of today, what you will find is that these concepts really form the core of what I'm about to talk about. Before I do that, however, I just want to take a brief divergence for any of you out there who say, I feel like I'm told what to do too much as a graduate student. So here we have this picture with our nice, restrained, erudite, grayscale nanocrystals. And this is not what they originally looked like. So the original nanocrystals were actually fuchsia and teal, which I thought was a very nice color combination. And Paul came down and said, you can't make a fuchsia and teal nanocrystal. It's not scientific. And I said, well, too bad. I rendered it, and it's fuchsia and teal, and it looks pretty, and we're going to keep it that way. Sadly, Paul was an assistant professor then, and page charges and color were really expensive. So we never published the fuchsia and teal nanocrystal. We only published the grayscale nanocrystal. But if you go to the web and search nanocrystal image, you can still find my fuchsia and teal nanocrystal skipping around the web. And sadly, I don't actually have the original anymore. All I can find is this one. Don't have the rock salt nanocrystal, but they were very pretty in fuchsia and teal. So put your stamp on your science. Don't listen to your advisor. Okay, back. Okay, back to the topic at hand. We started out talking about phase transitions, but really, this is a talk about energy storage. And so how are we going to get from phase transitions to energy storage? You probably have to wait about 10 minutes to get there. So let's start with the question of, how does it fundamentally a lithium-ion battery work? So we have to make sure that everybody's on the same page here. So all of you have rechargeable batteries. All of your phones have a lithium-ion battery in them. All of you probably spend half of your day cursing about the fact that your phone battery either takes too long to charge or the charge doesn't last long enough. And we specifically want to deal with that takes too long to charge problem. So in order to solve that problem, we need to figure out what is the origin of the long charging time in traditional lithium-ion batteries. And if you think about a battery, whether they are flat like in your phone or cylindrical as in some other applications, fundamentally, batteries are made out of layered materials, and they're just actually rolled up sheets. Okay, so you can roll them into a cylinder or flat, but fundamentally, just think of a sheet of anode and a sheet of cathode, and something separates them that is just meant to keep them from being electrically connected and shorting. So within that sheet of anode and that sheet of cathode, what you find is that both the cathode material and the anode material itself are generally layered phases. And the material that is stable with lithium in it is the cathode, and the material that is stable without lithium in it is the anode. And to charge a battery, you force lithium out of the cathode. You also force an electron out of the cathode, and you put both that electron and that lithium ion into the anode. Now you have a system in an unstable chemical state, and if you reconnect electrically the anode and the cathode, electrons will flow through whatever device you want to power, and lithium, why are you doing that? And lithium ions will move out of the anode and into the cathode to go back to the thermodynamically favorable state. And if we ask, in this entire process, what is the slowest step? The answer is solid state diffusion of lithium ions, both in the anode, in the cathode, in order to facilitate the charging and discharging process. So if we want to speed up a battery, what we need to fix is that slow solid state diffusion of ions. So there's a lot of people out there who are trying to make faster charging things. And in general, when people think about fast charging, they use what's called a Ragone plot, which is a map of energy density, that is energy per mass, versus power density, that is energy per mass per time. And what you see is that batteries have fairly high energy density, not as high as fossil fuels, but close, but that they are slow. Parallel plate capacitors are super fast. Nothing has to move except electrons, but they cannot hold very much charge because of electrostatic repulsion between those charges. And in the middle is supposed to be something called supercapacitors, which is a compromise between a parallel plate capacitor and a battery. And in many cases, those supercapacitors are the compromise that we need. But in reality, what we'd really like is all the capacity of a battery and just faster. Okay, so to think about how to get there, we really need to think about what is a supercapacitor. And it turns out that this literature is a mess. Part of it is really nice and clean, and part of it is really not. So when people say supercapacitor, many people think about electric double layer capacitors. So this is the same electric double layer that Dimitri was talking about when he was talking about DLVO type theory. And the idea is you take a conducting material, often high surface area carbon. Rick's group does a lot of beautiful work with this, as does Zheng Benduan's. And you charge up the surface of that electrode, and then you balance that charge by an ion in solution, and you make what is effectively a parallel plate capacitor at the interface between the solid and the liquid. And if you make your material nanostructured, your surface area can be high, and your capacity can be quite high. But fundamentally, you are still limited by electrostatic repulsion between these ions and these charges, limiting your total capacity. What we're going to talk about today is called a pseudocapacitor. And pseudo is the active word, because this is really halfway between a battery and a capacitor. So the idea is that we're going to do the exact same reaction that we do in a battery. For example, redox on a transition metal ion and balancing that reduced cation with a lithium ion to make a neutral ion pair. But we're going to do that battery-like redox at the surface or the near surface regime of a nanostructured material. And now we can have all the capacity of a battery, but we don't have that long-range solid-state diffusion of ions. So that sounds great, but it leads to some very fundamental questions. What is the pseudocapacitive length scale? How far into the material can ions move and not be considered diffusion controlled? Is it 1 atom length? Is it 1 nanometer? 10 nanometers? Maybe you're feeling generous and the surface is 100 nanometers. How do we define the pseudocapacitive length scale, or define where a capacitor stops and a battery begins? And maybe more importantly, how do we even measure what is pseudocapacitive compared to battery-like reactions? And I would say the challenge of that second question is one reason that the literature on this field is such a mess, because there's a lot of people who cycle batteries and say, well, they're fast, they must be a pseudocapacitor. But this doesn't lead to the fundamental insight that we would like. So it turns out that the measurement question is somewhat easier to answer, because if you take a CV curve, anyone who's probably done that knows that if you change the sweep rate, the rate at which you sweep the voltage, the current that you measure will vary with that sweep rate. And if you go back to the fundamental diffusion equations, you find that that current, as a function of voltage, should vary with the square root of sweep rate for any diffusion-controlled process. And so we will call all current that varies with the square root of sweep rate nu as battery-like intercalation. But if you just take classic parallel plate capacitor equations and transform them into the form of a CV curve, what you find is that the current should vary linearly with the sweep rate. And so we will say any current that shows a linear sweep rate dependence will be capacitive. And then, in the way of all physical chemists, you want to turn everything into a line, so we divide through by square root of sweep rate, and we linearize this, and you can pull out K1 and K2 constants from the slope and the intercept of a graph like this. And then, on a CV curve, you can quantitatively say at each given voltage what fraction of the current is capacitive, shaded in gray here, or diffusion controlled, shown in white. And what you see is at the peaks of the CV curve, they're mostly diffusion controlled. Everywhere else, they're mostly capacitive. And I should point out that this work and the basic development of this kinetic analysis was done by my close collaborator in this work, Professor Bruce Dunn in material science and engineering. And the vast majority of the work I'm going to show you today is actually a collaborative effort between our two groups. Everyone has keys. We spend a lot of time stealing each other's equipment. So you can take a CV curve and shade it like this, and I'll show you a lot of those. Or you can just take and integrate over the entire CV curve and just make a bar graph. And in this work on monolayers of titanium dioxide nanocrystals, you may think of titanium dioxide as a semiconductor or wide bandgap, but it can also be used as an anode for a lithium-ion battery. What you find is when the material gets to be less than 10 nanometers in diameter, it's about half capacitive. And if you do some super fast volumes and surfaces of a sphere, you find that that 50% capacitive corresponds to about the outer 2 nanometers of the nanoparticle behaving in a capacitive manner. And for most people, you see a little sigh of relief. 2 nanometers feels like surface. The world makes sense. Okay, so that's a nice result, but a monolayer of nanocrystals does not make a very big battery, and we want to eventually power cell phones and cars and power tools, and we're not going to do that with a monolayer. And if you take that monolayer of nanoparticles and just make it into a nanoparticle film, and not a thick film, about a half a micron thick, what you find is it's still half capacitive, all right? But the entire capacity goes down. And this is because the electrolyte can't access all the surface of those nanocrystals, and so they can't respond to the, they can't have the short ion diffusion links. And so to solve this problem, what we need is a better architecture for our nanoparticles. And what we've determined over a fair number of years of working in this area is that the ideal architecture is a nanoporous network of nanocrystals. And the idea is that you want very high internal surface area created by the fact that you've got very small nanocrystalline building blocks. You want the electrolyte to be able to access all those surfaces, so you need porosity to diffuse the electrolyte in there. But then more importantly, the battery community decided a long time ago that micron scale was the right size for battery materials, because if they're less than that, the electrical conductivity begins to dominate. And so you need to connect those nanoparticles into an electrically interconnected micron scale grain so that electrical conductivity does not become rate limiting. So making holes in things is one of our favorite things to do. And we use a lot of different methods to do this, but they're all basically involve block-copolymer templating, either using diblock-copolymers that make spherical micelles or polymer colloids that are preformed, and then co-assembling either inorganic precursors or preformed nanocrystals with those organic spheres to make inorganic organic composites, and then removing the organic to make nanoporous inorganic materials. And we can make them ordered or disordered. And sadly, for beautiful TEM images and SEM images out of my group, the disordered ones work just as well for batteries as the ordered ones, so we don't make a lot of ordered materials anymore because it's only pretty and not actually useful. Okay, so let me just give you a quick example of how this works. Here's those very same titanium dioxide nanoparticles that we can make into periodic arrays, and we can also make a porous network from sol gel precursors. The difference here is that these walls are solid, and these walls are made up of individual nanoparticles so that the surface area is high here and the surface area is low here. And what we find is that here's the data I showed you before, monolayer of nanoparticles, thick film of nanoparticles. Here's our porous network using a sol gel precursor with low surface area, and we find that the capacitive fraction is quite low. And here's the nanoparticle-based material, and it's essentially identical to the monolayer of nanoparticles. So we say, okay, we've got an architecture. Now let's go figure something more fundamental out, like what is the pseudocapacitive length scale? So what we did is we took and we made a network of non-redox active nanoparticles, ITO, just oxide conductors. And we assembled them into a porous array, and then we coated the surface with a battery material, vanadium pentoxide, using gas phase deposition in collaboration with Gary Rubloff's group. And we sort of arbitrarily said, let's coat them with a thin film, 2 nanometers, and a thick film. And we picked the thick film because that's about as thick as we could go without blocking the pores. And we picked the thin film because 2 feels like a nice number for surface pseudocapacitance. And here's our initial nanoparticle array, which is disordered but homogeneous in its pore size. And we said, this will be a pseudocapacitor, and this will be a battery, and the world will be happy. And we looked at it and we said, this is indeed a pseudocapacitor, and this is indeed also a pseudocapacitor. And that tells you that the pseudocapacitive length scale is not the same in every material. And if you stop and say 7 nanometers in from 2 sides of a material, that's 15, 14 nanometers. That's getting to be a respectable size nanoscale material. And that opens up the possibility of cycling the entire volume of a nanostructured material in a capacitive manner. And this leads to a concept called intercalation pseudocapacitance that really upsets electrochemists, because intercalation and pseudocapacitance should not be said in the same sentence without the word not. But we first used this word to describe moly trioxide, which is a beautifully ordered sol gel-derived material that we made that showed almost entirely capacitive charge storage, even though the walls were 20 to 30 nanometers thick. And we said, well, this is certainly not all surface. The term was actually originally coined by Conway, who was the original writer about pseudocapacitive charge storage, but he did not have any real examples of intercalation pseudocapacitance. So our favorite intercalation pseudocapacitance material is niobium pentoxide. Niobium pentoxide is extraordinarily fast. Here we show an example for beautifully ordered porous niobium pentoxide, which is dominantly capacitive. But in fact, niobium pentoxide is dominantly capacitive in any form, ugly or beautiful, up to something well over 100 nanometers in domain size. And we really scratched our head thinking about niobium pentoxide, and we asked, why is it pseudocapacitive up to such a large size? And a theorist friend of ours, Vidvid Zozelins, who was here at UCLA and is now at Yale, said, I'll explain niobia to you. So if you look at the crystal structure of niobia, niobium only occupies 2/3 of the lattice sites, and the other third is vacant for charge matching reasons. And so lithium can go sit in the vacant sites. And then Vidvid's calculated the rate at which lithium could hop between lattice sites and found that it was extremely fast. And so we said, oh, well, maybe intercalation pseudocapacitance is just a balance between lithium diffusion rate and total diffusion distance. So every material has a pseudocapacitive length scale, and in titania that may be 2 nanometers because lithium moves very slowly, and in niobia that may be 100 or 200 nanometers because lithium moves very quickly. But of course that's not the whole story, because I have another half hour, 10, 25 minutes here to talk to you, so there'd better be more to say. And the answer comes down to a topic that I brought up at the very beginning of this discussion, which is in niobium pentoxide, lithium sits in a vacant site. And so in order to put lithium into this material, the crystal structure does not need to rearrange. But if you look at most battery materials, the crystal structure without lithium and with lithium are different. And in order to insert lithium into a material, you need to nucleate a lithiated phase, and that lithiated phase needs to propagate throughout your material in a first order solid-solid phase transition. And any nucleation and growth process is fundamentally diffusion controlled. And so if this happens, the material is a battery. But in a number of nanostructured materials where we were trying to reduce the diffusion length, we found highly capacitive behavior, even though we knew those materials had phase transitions in the bulk. And so the question to ask is suppression of phase transitions in nanoscale materials at the root of intercalation pseudocapacitance? So we said, let's go look. Let's go find one of the materials that we've made that's really fast and look at the phase stability. So our first identification of this phenomena was in moly dioxide. And we can make nice nanoporous versions of moly dioxide. And we can buy micron-sized powders. And indeed, we find that the nanoporous moly dioxide is highly capacitive. Shaded region is capacitive. And the micron-sized powders are mostly not capacitive. And then we took materials. This is all ex situ diffraction. So we cycled it, took it out of the cell, took diffraction. We found that in the bulk, there is a clear first-order lithium intercalation-induced phase transition, and then a back phase transition as you take the lithium out. And in the nanoscale material, nothing happens. Now, other people, not this audience, might say, oh, the peaks are broad. Can you really see anything in broad peaks? You guys are all used to broad peaks. But indeed, even with the broad peaks, nothing's happening. The phase transition does not occur. And so this led us to the idea that perhaps suppression of phase transitions in nanoscale materials is really at the root of intercalation pseudocapacitance. And I'm going to come back to moly oxide towards the end of this talk. So just keep these ideas in line. OK, so with this, we said, OK, we understand. We can now define design rules for intercalation pseudocapacitance. So what do we need? Well, the first thing we need is porosity so the solvent can get to our nanoscale material. But then we need a combination of nano-sized building blocks for short diffusion lengths and high ion diffusion constants. And these two need to be matched so that in a short period of time, you can diffuse throughout the entire particle. I should actually point out, what do we define as a short period of time? Well, in a battery, you have liquid state diffusion of lithium from the cathode to the anode. And while things move very quickly in liquids, it's still a pretty long distance they have to travel. And that's a few seconds time scale. So if you're faster than a few seconds, the liquid state diffusion becomes rate limiting, and that's really as fast as you can ever go. And so we're going to define diffusion controlled as the solid state diffusion is not the defining rate limiting step. So we're always looking in the time scale between a few seconds, longer than a few seconds, up to hours if we want. OK, so the first part of our definition is this short diffusion length and high diffusion constants. And the second part is a structure that either doesn't need a phase transition or has suppression of phase transitions due to finite size effects. And then, by the way, we need high electrical conductivity. So how can we create a material that has this? So I should be able to design this, but I'm going to start out designing this because it's a lot easier. If you want to increase the diffusion constant of a material, what you want to do is weaken the interaction between lithium and the host. And lithium is a hard cation. And so the easiest way to weaken that interaction is to go from a hard anion, like oxygen, to a soft anion, like sulfur. And so we go from moly oxide to moly sulfide. And I must say that unlike Dimitri, we are not awesome inorganic chemists. And we don't want to work with crazy sulfide precursors in solution. And so how do we make our sulfides? We make oxides that are beautifully ordered using sol gel methods. And then we throw them in an oven with hydrogen sulfide, and we convert them to oxides. And the beauty of this, there's a gain over the people who are super tough inorganic chemists. The advantage of this is that the oxides that we can make are three-dimensional tunnel structures, and so it's very easy to make 3D nanostructured networks. But moly sulfide is a two-dimensional structure, and if anybody's made it, you know the only thing in the world you can make is layers, because it makes layers extremely quickly. But if you do a solid-state conversion from oxide to sulfide, you can entirely retain the nanoscale architecture of the oxide in the sulfide material. So this is low-angle diffraction scattering off the pores, and you see it's basically identical. Pores are a little smaller because the volume of the moly sulfide is bigger. These are thin films. We can also make nanoparticles, starting with moly oxide nanoparticles. And now you can do TEM, and you can see how the poor moly sulfide layers wrap themselves up any way they can to squish themselves into the little nanoparticles. And then you can take these nanoparticles and assemble them into nanoporous networks. So once we have these both thin films and powders of nanoparticles in porous networks, we can now begin to look at the cycling behavior of these materials. Quick diversion, anybody who works with moly sulfide knows that it is a semiconductor. And I told you that high electrical conductivity is of paramount importance. Luckily, nature is kind to us in this case, because when you intercalate lithium into moly sulfide, it undergoes a slow nucleation and growth, kinetically limited but irreversible phase transition from a semiconducting 2H phase to a metallic 1T phase. And so we cycle this material slowly, drive this phase transition, and then use it in the metallic 1T phase. And so all of the work that I will show you is on the high conductivity metallic 1T phase. So if we do this, we can make extremely fast charging battery systems. So if you're not familiar with this C notation, 1C is complete charge in an hour, 100C is complete charge in 1/100th of an hour, or 36 seconds. And you find that these materials show 100 milliamp hours per gram capacity in just a 36-second charge, which is extraordinarily high for that short a charge time. The materials are dominantly capacitive, and they show extremely long cycle lives, 10,000 cycles. So, okay, question for the audience, not my group. Why do batteries die? Why doesn't every battery give you 10,000 cycles? What kills a battery? Hint, there's one main topic to this talk. Huh? Not lithium-ion battery, not a lithium metal battery. We're not anywhere near potentials we're going to get dendrites. Hint, there's a topic to this talk. Repeated phase transitions is the dominant thing that kills a battery. Taking a material back and forth through a phase transition just rips the atoms apart. So when I see 10,000 cycles, I say this material must not be undergoing a phase transition. And so indeed, we can put this material, we can punch little holes in our batteries, we can go down to the synchrotron, and we can do diffraction while we cycle these materials. And you find in bulk molysulfide that as you cycle it, a second peak appears, and these peaks shift. And as you take the lithium out, the second peak goes away, and the peak shifts back. So you have a symmetry-breaking phase transition. In the nanoscale material, absolutely nothing happens. Symmetry change, so phase transition. So just as the walls of the molysulfide rearrange slightly to accommodate the presence of the lithium in the van der Waals gap. So it's rearrangement of the molysulfide bonding. And that's the problem, is because that means the covalent bonds in the material are rearranging, and you're making defects.
That's what you meant by breaking the atoms apart?
Yeah. Breaking bonds. Yeah, sorry, thank you. Okay, so how do you make things harder for molysulfide? You go from lithium to sodium. Sodium is much bigger than lithium, and in the bulk, you can cycle it with sodium, but it actually shows two phase transitions in a process called staging, where you put in half the lithium and the structure rearranges, and then you put in the other half of the lithium and the structure rearranges even more. Yet for these nanostructures materials, you find even with sodium, they are dominantly capacitive. And here's the analysis I showed you before. This is another assumption where you do an extrapolation to infinite sweep rate, and you get basically the same capacitive fraction using both analyses. So this is robust across assumptions. If you go to do diffraction, in the bulk, you find here's the first phase transition, these two peaks join. Here's the second phase transition, this peak splits. You undo the second phase transition, you undo the first phase transition, and you see hysteresis in the peak positions. That's in the bulk. If you go to nanoscale materials, again, you find almost no structural change and no hysteresis in the peak positions. So we can say, I think maybe we begin to understand what is the fundamental nature of a pseudocapacitor. And more importantly, technologically, you find you are quite literally outside the box. You can cycle the full capacity of an electrode material, but with much higher power densities than normal batteries. So you say, great, go start a company. We have. We'll see what it does. But there's a problem, because all of these are anodes. And to make a battery, you need an anode and a cathode. And so what do? The problem with cathodes is that they need to be made at very high temperature, the same problem that Dimitri was telling us before for highly luminescent materials. Because cathodes have lithium in them, you have multiple cations, and you need high temperatures to get all the cations to order. So how do we solve this problem? Well, one simple solution is to go to one of the few cathodes that does not require high temperature. Lithium manganese oxide crystallizes just around 500 C, and so we can make nice porous materials with reasonable ordering. And when we do this, we find that indeed they are highly capacitive, and they lose very little capacity as you sweep faster. But what you find is the capacity is very low, and that is due to a known problem in lithium manganese oxide, which is that the surface is inactive. Manganese 3 on the surface disproportionates into manganese 2 and manganese 4, and manganese 2 sits in the lithium site, and then the lithium can't cycle. And so in this case, we actually have no surface pseudocapacitance. We only have intercalation pseudocapacitance, because the surface is inactive. So I said to my student, could you please make some bigger lithium manganese oxide? And this individual did not love solution phase synthesis. So he took his beautiful, absolutely homogeneous 10 nanometer domain-sized nanoporous lithium manganese oxide, and he threw it in the oven at 700 degrees C for 1 minute, and all the grains grew to about 20 nanometers. And then at 800, and they grew to about 40 nanometers. And then at 900, and they grew to about 70 nanometers. So these are not the most homogeneous materials, but they do give us a progression of steadily increasing domain size in a self-similar nanoporous material. And what you find when you look at the electrochemistry of these materials is that indeed, as you get bigger, the slow sweep rate capacity goes up. You've gotten rid of surface area, you've gotten rid of inactive sites, you have higher capacity. And by the 70 nanometer material, this is basically the bulk capacity of 120 milliamp hours per gram. But then as you go to higher C rates, you find these curves all cross, and it's a little hard to look at. And so it's easier if we normalize them. And what we find is that 10, 20, and 40 nanometers all show the same kinetic behavior, and 70 nanometers shows different behavior, suggesting these are one thing, and this is something else. And if you do kinetics, you find that all of the small ones are dominantly capacitive, and the big ones are much less capacitive, suggesting these are one thing, and this is something else. And if you look at cycle life, all the small ones have thousands of cycles, cycle life, and the big ones decay much more quickly. And then you can go to the synchrotron, and what you find is for large-sized particles, the data shows a discontinuous first-order phase transition. And for the small-sized particles, they show no discontinuous change, and in fact, a much smaller overall shift in peak position. And so you can say, fundamentally, this is a crossover from a battery to a pseudocapacitor based on a crossover from the existence to the suppression of phase transitions in finite-sized material. And now you might say, we really do understand what defines a pseudocapacitor. But I can't leave you thinking that this field is solved, because every answer provides more questions. And so I want to now go back to anodes and go back to that moly dioxide. Because with this work we said, all right, there's a critical size. Nanoparticle people love critical sizes, where things cross over from one behavior to another. We said there must be a critical size in every material that shows a crossover between battery-like and pseudocapacitive behavior. So let's make things that have a really large range of sizes. And it turns out that using block copolymer templating, it's not always so easy to make a really large range of sizes. But using PMMA colloids, we have more flexibility. And so in this work, we used a polyoxometallate molyoxide precursor and PMMA colloids. We put them in solution. If you just dry them, you find the PMMA colloids always crash out before the precursors, and you never make good materials. But if you freeze dry them, you can freeze them all together and then lyophilize them and heat them to convert them to mesoporous powders. And the beauty of this is that if you put in only a few colloids, you're left with very thick walls. And if you put in a whole lot of colloids, you can make very thin walls. And so you can systematically tune the domain size of the material just from the ratio of precursor to polymer template. And what you find is, as you go from big to medium to small, is that there are systematic changes in the charge-discharge kinetics. So in red, we have the biggest ones, and we find their initial capacity is high, but it drops the fastest. Intermediate, somewhat intermediate behavior. And we go to the smallest ones, they start with slightly lower capacity. That's because moly dioxide spontaneously oxidizes to moly trioxide in air, and the moly trioxide is not active in these potential ranges. And so we find that the capacity is a little smaller, but it loses a lot less capacity. So the yellow is the fastest curve. And then we can again go to the synchrotron and ask, how do these three sizes behave? And what we find is, for the largest size, we see our nice, clean, first-order intercalation-induced phase transition, which agrees with the idea that these are kinetically slower electrode materials. When we go to a medium size, what we find is the initial peak position is exactly the same as for the large material, but now the transition has gone from first order to second order. That is, we see a smooth evolution in the peaks. So for those of you who don't think about phase transition, what this means is, in the large size, we have nucleation and growth. We have a nuclei of the lithiated phase, which then propagates across the material. So we have two-phase coexistence and a discontinuous phase transition. For the medium size, we put in lithium randomly, and so we homogeneously evolve the system from the moly dioxide crystal structure to the lithium moly dioxide crystal structure. Okay, but there's a smaller size yet. So what happens when we go to the smaller size? In this case, we see complete or near complete suppression of the phase transition. Now the structure doesn't change. We still put in most of the lithium, but the crystal structure does not respond at all. We keep the delithiated crystal structure and we add lithium to it. And so I would say that although we understand a lot of things about these structural changes, there's still a lot more to understand in terms of what fully defines pseudocapacitive charge storage. So here's just a summary of this, where we can see that in large ones we have a discontinuous first order phase transition, medium we have a second order phase transition, and small we have suppression of phase transition. So in fact we have two critical sizes that we now have to decompose into kinetic and thermodynamic effects. Okay, so before I end, I want to quick tell you one more story, because I think it just adds to the beautiful complexity of this world, which is to say, we said, all right, we really need more pseudocapacitive cathode materials. Let's go to some of the fastest systems that we know. And some of the fastest systems are all based on phosphates. So lithium iron phosphate. In this case, we looked at lithium vanadium fluorophosphate. The fluorine is used to increase the potential to make it a higher voltage cathode material. And my student developed some really beautiful methods to make nanoporous lithium vanadium fluorophosphate. The problem with fluorophosphates is that they lose oxygen if you don't have a fluorine source in there, but it's hard to get a fluorine source in while you're still templating. And what she did is she used Teflon colloids as the template and the fluorine source. Still in review with Paul. Hopefully it's doing well. So in this case, she was able to make beautiful homogeneous porous lithium vanadium fluorophosphate, good surface area, and this material is crazy fast. High capacity, 100 milliamp hours per gram, 30 C, not 100 C, but cathodes always have lower capacity than anodes, so this is really good for a cathode. So very fast kinetics, good capacity retention at high rates, very long cycle life, thousands of cycles, but if you look at the CV curves, they're flat, so they have plateaus. And what do plateaus tell us? Okay, so if you think about the simplest system, ice and water. The temperature of an ice-water mixture is pinned at 0 degrees C until all of the ice melts. In a battery, the potential of the intercalation reaction is pinned at the equilibrium potential as long as you have two phases present, as in nucleation and growth. And so the fact that we see plateaus indicates that indeed this is a battery-like system with a phase transition. And then we can do a kinetic analysis similar to what I showed you before, except we just do a power law fit and say the power can be anything it wants. If it's 0.5, it's a battery. If it's 1, it's a pseudocapacitor. And we find that for all the redox peak, the power is very close to 0.5, again indicating that this is a battery. And then finally, we go to the synchrotron and do diffraction. And indeed, even in these very small sized materials, we find clear lithium intercalation-induced phase transitions, 2 of them, as we cycle this material. And so fundamentally, nanoporous lithium vanadium fluorophosphate is a battery and not a pseudocapacitor. And the question then is, why is it fast? And our current hypothesis, which is not fully proven, has to do with the fact that in lithium vanadium fluorophosphate, which is a tunnel structure, the tunnels are open in both the lithiated and the non-lithiated phase. And so lithium diffusion is not pinned to the kinetics of the phase transition. And so while the phase transition may be diffusion controlled, the lithium intercalation and deintercalation can occur in both crystal structures. And so your kinetics of reaction are not limited by your kinetics of phase transition. But fundamentally, you can pair these fast batteries with true pseudocapacitors. Here's our niobium pentoxide, our favorite pseudocapacitor. And indeed, you can make fast charging overall batteries. This is half a battery, half a pseudocapacitor. But as an overall system, it's extremely fast and gives a really impressive practical voltage for a battery capacitor hybrid system. Okay, I think I am way over time, and so let me conclude. I hope that I have showed you that we can make nanoporous pseudocapacitors with optimized both atomic scale and nanoscale structure, and that we can get high rates and reasonable capacities. We can make both anodes and cathodes, and I want to just point out there was a poster by Tori Basili, who's in my group, on another really impressive fast-charging cathode that I didn't want to overlap and talk about today. So please visit her poster during the coffee break. And I think the most important thing, and the thing that I want to thank Paul for, is the concept that suppression of phase transition in finite-sized systems, combined with shortened diffusion length, is really the key to understanding this system, and that doing experiments where you understand fundamental things, like phase transitions in finite size, can really lead to practical understanding about useful systems. And then we just end with a cautionary note that not all fast charging things are batteries. our pseudocapacitors, and that we need to understand the details of each system in order to move these technologies forward. So let me end by thanking my group. I have a truly phenomenal set of students who did all of this work and many other works on a lot of other exciting systems. But today, I want to just flag the students that are here, 2 students who have left my group, John Cook and Ben Lascelles, and then a bunch of, well, I guess Terry's left too, but only recently. So Terry Lynn, who's actually now up at Berkeley, you should look for her. She's at LBNL. And then we have, I guess we need a new group picture. Yan Yan has also left. She did a lot of the work on lithium manganese oxide. And then we have Yi Yao and Danny Robertson, who did all the work at the end on the in situ moly dioxide. This is all, the majority of it has been a collaboration with Professor Bruce Dunn, and it's supported by the Department of Energy, and I want to thank you for your attention.
We had technical difficulties, got off to a late start, but certainly let's have a question if there are questions.
For fluorophosphide materials, I think they are very they should be insulating electrically to some degree, the material itself. To what degree it's a problem to shovel charge to and from the grains in batteries?
So all the phosphides are fluorophosphates are insulating, and lithium iron phosphate is also highly insulating. And so when we make it, we actually put in some extra carbon, and we graphitize that carbon on the surface. And so you have to put in a little bit of extra graphitized carbon in order to get enough electrical conductivity to use that whole family of materials. So it is a big problem, and it was the technological problem with building those into real systems, and it was solved by carbon coating. So now that's what everybody does.
So can you also comment on the surface redox pseudocapacitors? You mainly focus on intercalation, right?
So it's all a continuum. So in the world there is this division between surface redox pseudocapacitors, where you in theory are doing redox only in the outer 1 atom layer of materials, and intercalation pseudocapacitance, where you're intercalating into the bulk of the material. But in reality, there is a pseudocapacitive length scale for every material, and that length scale is defined by the lithium diffusion rate and the distance over which you can do redox chemistry without inducing a phase transition. And so for some materials, that distance is sufficiently short that we call it surface redox pseudocapacitance, and assume that the redox is really only in the disordered layer on the very surface of the material. And in some materials, that distance is a significant ways into the material. And probably for the vast majority of materials, it's a horrible mess of just a tiny ways into the material and dominantly a surface process, but a little bit of a bulk process as well. And so I say, for you theorists working on this problem, I have no way of simplifying it, because it really is a complicated pathway where the diffusion length is controlled by many phenomena, and they all have to be considered.
Thank you very much.
I'll just talk. So I have the honor of introducing our next speaker, Professor Munji Bawendi. Professor Bawendi is the Lester Wolf Professor of Chemistry at MIT, and he's sort of one of the pioneers and one of the founders of the field of the field especially associated with quantum dots and nanocrystals. Much like our honoree today, Professor Bawendi, he passed through UChicago, where he actually got to work, where he worked actually on some gas phase astrochemistry questions like H3+, and also some polymer dynamics. And then he switched directions and went to Bell Labs and worked with Lou Bruce, who, as you know, is sort of one of the founding fathers in this field, and also is where Paul passed through as well with working with Lou Bruce. So I'll just relate some personal. I was a postdoc with Professor Bawendi with Munji, and I got to learn a lot of different things. And I was really excited to start working with him because when I was doing my graduate work, I started thinking more about quantum dots and cadmium tellurium nanocrystals. And I went to talk to Dimitri, who graciously provided us with some quantum dots to start doing some spectroscopic studies of them. And I had some very deep questions about what is the S and P and D states in these systems? How do you think of the electronic structure? How do you think of the higher energy states? And Dimitri pointed me to a paper from Munji's group and with David Norris that kind of explicated everything and kind of went through in great detail for many different sizes. And I read this paper with so much sort of Talmudic detail that I ended up going to interview with Munji, and I said, and I kind of started talking about this paper, and it was from like 92 or 93, and he looked at me and he's like, yeah, and I clearly remembered way more about the paper than a lot of other people do. And the other funny part is, no, just kidding. It's actually still a very important paper. But the other funny part of it is that I had pulled up this paper and I printed it out, put it on my desk at Chicago, and I'm sort of sitting there. And at the time we had Graham Norris, who's David Norris's son, was an undergraduate doing research with Greg, my PhD advisor, and I didn't even know that he was related to David Norris, and he's like seeing that I'm reading papers from that his dad wrote in graduate school. And so you kind of get a sense of how small this world is and how small this field is and how really and generally supportive it's been for new faculty and new people across the board. So without further ado, I want to just have Munji come up and have a chance to give us talk and tell us a little bit about the sort of new directions in nanocrystal photophysics that he's been pursuing in his group. And so thank you very much.
So now how do I get it to the
Just
right top?
go to the first slide
And then press here.
yes.
Okay, this seems to be working. Okay. Let's see. Well, it's really my pleasure to be here to give a talk in honor of Paul. First met Paul when I was a graduate student. The mic, yeah, let me turn that on. Let's see. Is it on now? Yeah, okay. Okay, cool. I was a graduate student. Paul was a postdoc at Bell Labs. And I had been working mostly in gas phase infrared spectroscopy. And I didn't do any synthesis or anything like this. And Paul was really my mentor in opening my eyes to the fact that you could do spectroscopy in the visible, which I had never done before. And it was a lot easier in some ways than the infrared. And also you could mix chemicals together and make molecules. And one of the things we did before was we only bought stuff that was out of lecture bottles. And so the whole world of liquids and solids and beautiful light. I'm very happy to be here also because Paul not only was a pioneer in the field in terms of the science, but I think without his leadership in the broader scientific community, I don't think we'd really be seeing so much activity in our field. So that's really a credit to Paul for this. I'm going to talk to you about probably one thing, but maybe two things. Since I was asked to talk about the bioimaging, but this is what we're also exciting about today. So I'm going to start with looking at particles as a potential source of quantum light, and I'll explain to you what I mean by that. So let's start with that part right here. And so the particles I'm going to be talking about are perovskite particles, and as many of you know, these perovskite materials have been really interesting in the last 10 years or so. Initially for solar energy, solar cells, thin film perovskites. The power conversion efficiency now is 25.2%. And the lifetimes are getting longer. When I first started working in the perovskite solar cell film, I thought, first of all, I didn't want to work in that field because it was like the beginning of the OLED field where you made one measurement and you destroyed your device. And I thought, this is a crazy thing, this will never lead to anything at all. But I got dragged into the field, kicking and screaming by students, and here we are today with a field that's really getting very much closer to something that's a real material. But anyway, so the perovskite as a material for solar energy is really super interesting, and it turns out it's just as interesting in a small particle form. And what I'll be talking about are cesium halide or cesium lead halide particles, largely developed by Maxime Kolovenko at ETH. And I think there's a path from Maxime. Did he work with you, Maxime? Oh, Dimitri, yes, yeah. But it's all connected somehow. There's a path. All paths lead to Paul. Okay, so and so these particles are the ones I'm going to tell you about are actually not completely quantum confined. They're about 10 nanometers in size, and it turns out that for these particles, the sweet spot for what I'm going to talk to you about is something which is a little beyond the quantum confinement, enough to hold one exciton in there, but and not so big as 2 excitons would fit comfortably in there, because you want to take advantage of the super radiance effects that you have when you're slightly beyond the quantum confinement effect. Okay, so let me give you a little bit of motivation here. What do we want to do? We want to create something that's an ideal single photon emitter, not to say that we're here yet, but this is on the path to doing it, where this emitter gives rise to a stream of photons where the single photons are indistinguishable from each other. And we want them to be at a high repetition rate. So what does it mean in practice? It means in practice that we want the T2 time, or the dephasing time here, to be twice the population time. And this is an area of large interest to quantum photonics, as there are a lot of people working in that area for a bunch of potential applications. And the dream is to form an array of these objects that just emit these streams of single photons that are all similar to each other, so you can start playing some really interesting quantum optics games with them. So, and certainly you can do that in the gas phase with one atom that's not connected to any baths of any sort. But as soon as you want to make a device that produces these sorts of photons, then you run into the challenge of the solid state, which means that you end up coupling to baths. For instance, you've got a phonon bath, you've got a spin bath, you've got longer time scale, spectral diffusion, and all these things give rise to a pure dephasing term here, which then disturbs this nice transform-limited transition, which keeps the coherence between the excited state and the ground state. And then you end up with a series of photons which no longer have a coherence between them. Also, you may end up with reduced single photon purity. If you have multiple states, you can put multiple excitation in them, and instead of emitting just one photon, you emit 2 photons, and that also destroys your beautiful stream of single photons you're trying to create. And then you can get non-radiative decay paths, and so every now and then you try, or many times you try to excite your emitter, and instead of exciting and instead of emitting a photon, your emitter decays non-radiatively, and so you get a reduced emission quantum yield. You get essentially what we see as blinking in quantum dots. Quantum emitters have been around for a while in the physics community, and some of the most beautiful ones are made, for instance, out of indium gallium arsenide. This is one of these little pillars of indium gallium arsenide with a bunch of Bragg stacks in between them, and so the stacks basically make sure that they act as to enhance the output, and so you get a beam of single photons coming out, and you can get this so this is a measure of how close it is to being transform limited, to getting coherent photons coming out of it. And so this is 0.99 is as good as you can get. 1 is perfect. As long as you integrate this in a cavity, which means you take advantage of a Purcell effect to speed up the T1. This is also really nice because it's at 1.5 micron. You can, one of the problems with this is that you make one and you study it for 6 months, and it's great. But then you want to make a second one, and it's it may not be exactly the same as the first one. And so there's an issue of reproducibility. And so it's wonderful to do physics. And so we'd really like to have more of an opportunity to explore more materials that may be a little bit more scalable. So more recently, people have been looking at nitrogen vacancy centers in diamond or silicon silicon dopants also. And those have also good T2 divided by 2T1. And very good homogeneity in terms of the colors. But the diamond has a very high dielectric constant. And so it's actually hard to get the photons out. So they tend not to be very bright because of this. It's hard to drive them electrically since diamond is such a great insulator. And you can't change the emission color. It is the color of the vacancy. So there are many other alternatives out there. For instance, you can look at some defects in zinc oxide or defects on the surface of carbon nanotubes, some defects in HBN, for instance. HBN, we've looked a little bit at these. Turns out every defect is different and uncharacterizable or uncharacterized. It's really hard to work with. And then we have our quantum dots here, the usual cat selenide. And if you look at the pros and the cons, and they all have pros and cons, and there's no perfect material for this, that's for sure. If you look at the cat selenide, all the pros, like they're easy to make, they're color tunable, et cetera, et cetera. The problem is that they have very incoherent emission. The lifetimes are very, very long, and orders of magnitude longer than the dephasing time. And so your T2 over 2T1 is really tiny. So those materials, you might as well forget about them. And so we never really thought about nanoparticles as signal sources of coherent photons until we started doing work with cesium lead halide. And it sort of circuitous how we got there. And it turns out that this material is very different from every other quantum dot that we've ever seen in terms of its electronic structure and its optical properties. So it's just like for the solar cells, it's kind of magic. It has properties that we would never have expected. OK, so what gives rise to these properties? If you look at the semiconductors we're used to working with, like the CAD, the 2.6s or the 3.5s, we always talk about there's always these traps that are in the middle of the gap that give rise to non-radiative defects or slow recombinations. And those are largely gone in the late halide perovskites. And more importantly, if you look at the structure at the band edge, in the 2.6 materials or the 3.5s, the lowest state is a spin forbidden state. So if you go to low temperature, and all these experiments are done at low temperature, at cryogenic temperatures, you trap out in this spin forbidden J equals to 2 states, and you end up with lifetimes that are on the order of microseconds or even longer. And that's no way to get a good quantum material, quantum light emitter. Your dephasing times are still going to be on the order of 100 picoseconds or so. And so the difference between your T2 and your T1 is so large that you might as well forget about it. However, for the perovskite nanoparticles, and this is still kind of debated, but it's looking like the lowest state is a spin allowed state because of the symmetry breaking. Rashba effect, the internal electric field, breaks the symmetry and changes the order of the spin forbidden and the spin allowed state. And you end up with an extremely bright transition from the lowest excited state at low temperature. completely different from every other semiconductor we looked at as a quantum dot. And so now T1 becomes, instead of being microseconds or milliseconds, becomes much, much faster, and it becomes possible for this T1 to be on the same order as the curative phasing or the T2 that we're trying to get to. Okay, now we also have to figure out, are they going to be a good material for single photon emission? So we want both fast emission, or this T2 over 2T1 to be close to 1, but we also want them to be able to give a stream of single photons one at a time, and not bursts of photons, and we want them to have high quantum yield, et cetera. So I'm going to go to a little bit of detail into the spectroscopy that we do to test these ideas, that they can be good as a source of single photons. This is called the single photon purity, and also that the single photons that come out of them are pretty coherent. The field was really started by spectroscopists trying to understand the materials through their interaction with light. So this is, in a way, going back to the beginning of the field, where we're trying to see how light and this material interact with each other. So in the course of the last 20 years or so, my group, led by many incredible graduate students and postdocs, just being one of the latest ones, spent a lot of time developing ways to characterize the spectroscopy of single quantum dots. Initially, looking at quantum dots on surfaces, but this has some issues. There's a user selection bias, for instance. You get poor statistics if you have to spend a lot of time on each dot. And more recently, combining the methods of single molecule spectroscopy on surfaces with solution, being able to look at single quantum dots in solution and extract information about their spectroscopy. In this case here, we're going to be looking at the yield of creating two excitations in one exciton, or in one particle, called a biexciton, using solution methods and extracting single particle information about that. And the nice thing about going to solution is that you no longer have user bias selection, which is nice. And you can even look at samples that are quite unstable, because your sample is constantly being replenished in your small volume that you're looking at. Okay, so this is essentially a fluorescence correlation spectroscopy experiment. So if you've done fluorescence correlation spectroscopy, you see you plot the G2, or the cross correlation. You have a beam splitter here. You've got a beam, your beam of photons come in here. You've got two detectors here. And you look at the cross correlation between these two guys, and you see a set of time scales. So if your time scale is very long compared to the diffusion time in the small volume that you're looking at, then you're looking at photons, pairs of photons that you're doing the correlation with, that are coming from different particles. Okay? The first photon comes the first particle that's in your small volume. That particle diffuses away. The second photon comes from a second particle that's being excited and that emits. At very, very, very early times, where T1 here is very, very short, and you're using a pulse laser, in this case here, you're looking at pairs of photons that are coming from exciting with the same pulse, with one pulse. Okay, one pulse comes in, and you get two photons that are coming out. That's a signature of having created a biexciton, or two excitations in one. And then there's the middle region right here, where the time scale is shorter than the diffusion time, but longer than the separation between your pulses. And that basically is two photons that are coming from the same particle with high probability. And then there's a diffusion time in your sample here that is usually measured by the biologist, for instance. This fluorescence correlation spectroscopy was invented in the 1940s. Webb, who's at Cornell, invented this. It's quite useful. But what people have generally not looked at is using a pulse laser and looking at this time scale right here, which is very short, and comparing the amount of signal that you get here compared to the signal that you use in the longer time scale when you're looking at pairs of photons from the same particle that come from separate excitons. So it turns out that this ratio of the signal you get at extremely early times when you're looking at the 2 photons coming from one pulse versus 2 photons coming from separate pulses, that ratio here gives you the quantum yield of the biexciton to the exciton. And that's a measure of the photon purity, of the single photon purity coming from your sample. And so you can now, because just like many particles, we have the power of synthesis, of altering the stoichiometry of the elements that are in there. And then you can begin to both look at the size difference as well as the stoichiometry of the halides that you put in these cesium-lead halide particles. And you find that there are 2 regimes that you can go into. You can have a biexciton quantum yield which is reasonably high for these cesium-lead iodide particles. And those would be good, for instance, for LEDs, where you want to drive the material really hard and you don't care that you have multiple photons coming from the same, in the same particle at once. And you want just really high brightness generally. And on the other side of the scale here, in these cesium-lead bromide chloride particles that are fairly large, you end up with a very low biexciton quantum yield, and so you can have very high single photon purity. OK, so that means that we want to be sitting right here where we have really 1 photon coming at a time from the material. All right, so now we can go and test for the coherence of these single photons that are coming out. OK, and we're going to do this at low temperature, at cryogenic temperatures. First, let me sort of summarize a few things. So, and this is at low temperature, so no longer in solution. So now we're back on a substrate where the particles are on sapphire or some other substrate here. Actually, it's not sapphire. It's crystalline silica. And we can do the single, this cross-correlation now. And this is the ratio of this peak right here to that peak. Tells you the level of single photon purity, and it's basically extremely pure. It's almost going all the way to 0 here. So the stream of single photon is very high. You can look at the quantum yield going all the way from room temperature to cryogenic temperature, and you have essentially unity quantum yield so it's a very bright source of single photons coming out. Great, 1 check mark. There is some spectral dynamics. There's a bath out there. There's charges moving around. So if you look at energy as a function of time, you see fluctuations in the position of the energy. This is quantum dot number 6 in this particular sample here. The brightness also fluctuates a little bit. I think we can deal with that eventually. Okay? It's not something that's new in the field. Other single quantum dots, other sources of single photons also show some. But it's much more stable than any other material that we've looked at as a quantum dot. The next thing we can do is look at this T1 time. Okay, we just measure the decay, the fluorescence decay of the material. And instead of seeing times that are on the order of microseconds, we see times that are on the order of 100 picoseconds. Extremely fast for this material. So this is, these are 4 different quantum dots from this sample, times ranging from 210 to 260, 270 picoseconds. Really indicative of, at least consistent with this idea that suddenly the slowest state is now spin allowed as opposed to all the materials that we had seen before. So completely different electronic structure at the low temperature level that we had seen before. So now this guy right here is orders of magnitude faster than anything we had seen before. And so that gives rise to some hope that maybe the pure dephasing time here may be long enough, or maybe we can eliminate this and have something which is close to transform limited, where the T2 time is close to the T1 time. Okay, how do we measure that? So the way we measure it is doing an experiment that also we developed over the last many years, which we call photon correlation Fourier spectroscopy. It's basic. Fourier spectroscopy is when you send something through a Michelson interferometer, and then you look at and then you interfere the 2 arms of the interferometer together, and you see whether or not, as you move one arm with respect to the other, then you can get back to the wavelength as you watch the constructive and destructive interference of the two arms as a function of this right here. So you can transform position of this of this delta here, the two wavelengths. If you do this one photon at a time, really what you're doing is you're putting one photon in here, and that one photon is interfering with itself, right? And so the amount of constructive or destructive interference as a function of the delta also gives rise to a measure of the coherence of that single photon that you're passing through. Right? So when delta equals 0, then that photon is overlapped completely with itself. And so that's going to be your highest level of constructive or destructive interference. And as you move delta, and so that photon becomes less likely to interfere exactly with itself. The phase difference between the beginning, I'm talking very quasi-classically here, the beginning of the photon versus the end of the photon, if there's some dephasing going on, it's not going to be as great of an interference as it would otherwise be. And so, and since you can move delta very, very slightly, you can, with piezos and stuff like this, this gives you a really high time resolution, actually, by being able to essentially take that photon and split it. Again, I'm talking very rudely in some way here. Split it in two and sort of move part of it ever so slightly in time with respect to the other one. So you can get time resolutions that are on the order of picoseconds, on the 1 picosecond time scale in an experiment which really doesn't have any ultra-fast components to it. OK, so this is a form of Fourier spectroscopy. But on top of that, we're going to add a correlation. We're going to correlate pairs of photons together and effectively to do that integral. This is a correlation of this is the energy here, and this is time here. OK, so when you do that, you form this. You look at the cross correlation between these two, between pairs of photons going on these two detectors, and at delta equals 0, you have they're anti-correlated, and as you increase delta, then you start to lose the cross correlation. You start to lose the phase. You can then change the time between the photons that you're correlating with respect to each other, and that gives you an idea of both the spectral diffusion that's going on as well as the broadening that goes on as the material is investigating the bath that's around it. So as a function of time here, then you're basically measuring the spectral correlation. And so you get something that's very narrow at the beginning, and then it opens up as you go to longer and longer time scales. OK, so this is what the data looks like. And remember, this is delta. This is the stepping that detector in space, in very short, and which translates to time. Right? The speed of light is 1 foot per nanosecond. So you can then get very small time resolution. And this is one of the first. This is quantum dot number 1. And so what you see then, when you look at this cross-correlation data, is you see first a very fast drop as you move your photon that you split in two, let's say, slightly apart from itself. And then you see a beating pattern. And this beating pattern is because there are actually two states that are close to each other in this quantum dot. And that photon that's coming out of the quantum dot has imprinted on it those two states, right? And so what you're seeing then is the coherence of those two states that are being created at the same time. And as a function of time, they're going to start beating against each other. And so you see the beating of these two states. And then this white line here is the loss of coherence as we're looking at the beginning and the end of the photon, let's say. And so out of this, then we can Fourier transform and get back a spectral correlation, which gives us
the separation in energy between those two states. There are 3 peaks because it's a correlation, spectral correlation, as opposed to a spectrum. And the white line gives us the T2, or the decoherence time of that transition. And you can measure it, and you can find that it's 70 or 80 picoseconds or so, which is really pretty long, much longer than we would expect for many other materials made out of quantum dots. And so we can do this with a bunch of other dots. This is dot number 2. You still see the same sort of thing. This is a different orientation. The lowest state is actually a triplet, and so we're actually starting to see a triplet structure here. But we again see a very kind of a long T2 relaxation time. And given that our lifetimes were so short, without doing any sorts of games of cavities, as we showed in the early motivation slide, where these indium gallium arsenide quantum dots made in the physics community were put into these Bragg stacks. Here with no Bragg stacks, no nothing, we get a T2 over 2T1, which is already 0.2, which is quite respectable for something that hasn't been incorporated into any sort of cavity to decrease T1. And just to give you a point of comparison, the epitaxial 3-5s, before putting them in cavities, are also on the same order, 0.15, 0.16, 2.2, or something like this. And when you put them in a cavity, then you can speed up T1 and get something that's close to 1. The NV centers, or here come the silicon centers, are on the order of 0.6. So the level of T2 over T1 is really kind of amazing for these materials, and it really tells us the magic of the solar cell material transforms into the magic of the quantum dot materials for optics. So where does one go from there? Well, one wants to put these dots in a cavity to get T1 to be much faster. And that's not very hard. You can have a Purcell effect on the order of 10, which is not a hard thing to do in a cavity. Usually people talk about Purcell effects and speeding up that lifetime by orders of magnitude. Here we only need 1 order of magnitude. This is a poor man's cavity would be able to do that. Then once you're able to do that, you want to prove that these photons are really completely coherent. And you do something which is called a Hong-Ou-Mandel experiment, or HOM experiment, where now you take pairs of photons, and you interfere them in a beam splitter, just like I was showing you before. And if these photons are exactly on top of each other spatially, and if they're indistinguishable with respect to each other in terms of color and phase, then they become entangled. And you read that the signature of having created an entangled photons, pairs of entangled photons, is that instead of coming out of a beam splitter randomly in the different directions, independent of each other, they come out as pairs. They either come out together in detector number 2 here, or together in detector number 1 here. So you change the path length of one of the photon with respect to each other, and then you can see the sudden change in the statistics of measuring the counts on your 2 detectors. And when you are at exactly the right spatial position, then suddenly your statistics change, and that's called the Hong-Ou-Mandel dip. And so that's the next test for this field here, to show the world, and the quantum optics people, that in fact this material is a proper emitter of quantum light. Okay, I have, I think, 10 more minutes. Is that right? Okay. So in the last 10 minutes, then, I'm going to completely switch topic, and I'm going to go back to the room temperature and talk about applications of biomedical imaging. So for a long time, we were working in the visible, it's beautiful light, et cetera. But somehow I was drawn back to my infrared roots before meeting Paul. Everything looks black and white. It's not as beautiful. But turns out that there's a lot of really interesting things. This is the shortwave infrared, which is between 1 and 2 micron, beyond what silicon can see. So these are indium gallium arsenide in-gas cameras that are used for night vision. And square light, as it's called, if you connect it to the technology, the SWIR technology or the night vision technology, is reflective, just like the visible light. but it also has different characteristics. It interacts with your sample in a different way than visible light does, because you're starting to see molecular interactions with that light. So for instance, water has a very strong absorption band at 1.5 micron, basically. And so just having the presence of water just changes your image dramatically. If you go further to the red of the SWIR into the mid-wave infrared, suddenly you're looking at something which is emissive. That's thermal emission. Okay, so this is still like visible and unlike the mid-wave infrared. An example of this effect of water being absorbed so strongly in the SWIR is if you have an apple with a bruise on it, which you can't see in the visible. If you go to the SWIR, the water, or the pool of water, the increase in the water density underneath the skin is clearly visible as a black spot because of that strong absorption band of water. Scattering is lessened. It goes like some strong power of lambda. And so as you go from the visible to the SWIR, and this you can see begins to see through smoke. And this is Sensors Unlimited that sells night vision equipment to the Army. And so this is why it's such an interesting wavelength for imaging other than biology. But it turns out it's also interesting for biology because there's a lot of scattering that happens in tissue. A long time ago, we were doing work with John Frangione at Beth Israel, and we were looking at this wavelength region, and we looked at this is the strong water band. This is transmission as a function of wavelength. There's strong water band here, 1.5 micron. And tissue is highly transmissive, actually, right before it, around 1,200 nanometers or so, 1,600 nanometers. And so we thought, we should be really looking in this area. And it turns out in the last 5, 6, 7 years, this has also become much more widely available to mere mortals. Because before then, there's something called ITAR, which is the International Traffic in Arms Regulation, which prevents anybody from basically buying these things without selling their firstborn, and or risking going to jail if somehow you happen to let a foreign graduate student look at your piece of equipment, even if it's for a nanosecond. So ITAR is a no-no. I mean, we're not allowed to buy anything that's ITAR restricted at MIT. And in 2013, there was only one camera that wasn't restricted under ITAR that was available for purchase. By 2017, there are now 34 cameras. What happened in between is that the self-driving car companies, or that motion, they want to be able to see in all colors. And one of the colors they're really interesting to see is in that wavelength range. And that has given motivation for the companies that sell these equipment to undergo the complicated process of deregulating their equipment. And they're starting to see the potential commercial potential of that technology. And as a result, the price of the cameras have dropped significantly, the form factors have dropped, and the efficiencies, and they're just, the cameras you can buy today are just so much better than the cameras you could buy 5 years ago for much cheaper. Okay, so one of the first things that was interesting is, there's this strong water band, and what is the effect of that strong water band? It turns out that that water band has the effect of increasing the contrast of your imaging. And that was not something we expected. And at first, I don't think the community understood that was. So if you look, this is an image that was pioneered by Hongji Dai, Stanford, of looking through the skull and skin of a mouse without doing anything to that mouse except anesthetizing it. And here we happen to have quantum dots, indium arsenide quantum dots injected into the mouse. And you can see the vasculature in the brain of the mouse with very good contrast. And so the question is it just because you're going to longer wavelength that you see such good contrast, or is it something else? And it turns out that you can begin to define a level of contrast. This is the sigma, or the standard deviation divided by the mean of your signal here. And as you go through, and this is the beauty of using quantum dots for this, because you can really cover that SWIR region really well, which you couldn't do with any other dye. You can do this with high quantum yield all the way across from 950 nanometers to 1600 nanometers. And what you can see is this sudden increase in contrast, which kind of stabilizes, and then it kind of starts to go down as you go to 1600 nanometers. And so as you look at this contrast, you see that it looks very much spectral-like. In fact, it is exactly fits on top of the water absorption. And the reason for that is, if you look at this here, you get a fuzz, which is your emission of your blood vessels, or your contrast, is being scattered by tissue, which is full of water, right? And as you move into the water range, then the scattered light that has to move longer distances than the light that comes directly towards you gets absorbed by the water, and that cleans up your contrast. So you clean up the fuzz because it's the water that's absorbing that fuzz. Okay, I'm going to skip this and go directly into a work here. So this is an experiment with Rakesh Jain's group at MGH, and we're looking at GBM, or glioblastoma, in mouse models. And again, this is to show the power of both quantum dots and this imaging, because what we can do is we can make particles that are composite particles of many quantum dots, maybe hundreds of quantum dots here, and that are bright enough that we can see individual constructs as they flow in the blood vessels. And why do we want to do that? So let me go ahead and begin the movies here. So this is an image of the blood vessels in the normal part of the brain. This is an image of microscopy image of the blood vessels, which is here at the edge of this glioma or glioblastoma tumor. And you can see these bright spots sort of coursing through the capillaries. And these are these big composite particles. And they're moving very fast. And if you look at the same flow, you can see here that here there's a particle that's just going back and forth. It's completely non-functional. Right? And the flow is also much slower. And you can do particle tracking velocimetry. You can actually track from frame to frame the position of the particles and transfer the data and actually quantify the flow rates in the different vessels. So this is what it looks like in the healthy part of the brain, and this is what it looks like in the unhealthy part of the brain. This is why it's so hard to treat solid tumors, because therapies just don't get there. And so part of the collaboration is understanding, first being able to image this, and then provide therapeutics to try to make this look more like this, and then to see if that has an effect on the therapies. Okay, now one last thing. Sphere quantums are great for doing this sort of thing. And I'm always interested in translating things to humans. And it's really hard to think about translating quantum dots to humans. But it turns out that even though quantum dots are really wonderful things, and you can make composites, and you can make big ones and small ones, and you can change the color, and they don't bleach. They have high quantum yields, 30% compared to everything else that emits in that wavelength range. There's one dye to beat them all, and that's indocyanine green. That's the first dye that was approved by the FDA in 1959. It's ICG. It has a peak at 800 nanometers in absorbance or in emission. And when you're talking about doing in vivo imaging, quantum yield is not the metric that's important. That's what we always used to think about, and that was just because we weren't thinking. The metric is brightness, which is a combination of quantum yield and absorption cross-section per weight or per volume of stuff you're going to put in that poor animal. There's only so much you can put in, right? And if you compare the brightness of this dye, and you just look at the tail of the dye in this region here, and you compare it to, this is the dye here compared to a couple other dyes. This is ICG looking at the in-gas camera. And even if you compare it to quantum dots, it's orders of magnitude brighter than the quantum dot in terms of brightness. And so we've done, now you can't multiplex because you're just looking at tail. There's no structure to it. But you can do all these other experiments that I had shown you. You can show the increase in contrast from the near infrared to the SWIR, and the mouse here, and the leg of the mouse, just with this clinically accessible dye. And these are a couple movies. I don't know if they're going to play. Well, anyway, ICG is used in the clinic all the time. There are more than 300 clinical trials using ICG in the visible, and it's such a simple switch to replace the camera, the silicon camera these days, with an in-gas camera. And from talking to the vendors of in-gas cameras, I know that a bunch of people at the Harvard Medical School have now started to use ICG in the shortwave infrared. Okay, my group, unlike California, it snows, and we enjoy the snow. We like to go skiing close by. And these are wonderful students. I think Justin, no, Justin's not. This is a more recent picture. Okay, thank you very much.
So I think we have time for at least a couple questions, and I will leverage my ability to go first, because I always want to do that.
Okay.
So the radiative rate is extraordinarily high in the perovskites.
Yes.
And I could argue there are two things that go into radiative rate.
Yes.
One is the density, the photon density states, and the density states of how many levels you have to emit from. And the other one's that transition dipole moment.
Yes.
What are the transition dipole moments enormous?
So I mentioned at the very beginning, and I didn't stress it, that these are actually not quantum confined particles. These are a little bit bigger than quantum confined particles. They're 10 nanometers to a side. And they're a little bit like J aggregates. You get a super radiance effect because of that. You delocalize your exciton over the whole volume. But the volume is small enough that you can't actually put two excitons easily in there. And that's what makes it such a good single photon source, but also have a very fast radiative rate. When you quantum confine, it actually gets slower.
Okay, I have to think about that. I'm not sure I agree with you, but I have to think about that. Okay.
I'm sure you're right, actually. Whatever you're thinking.
Do we have another person? Would you like to give a talk, or will we go? Oh, yes, Marie.
So related to this question, you showed this series where there is an increase in the bi-exciton to exciton ratios when you go to bromide, and it decreases. Yeah. What's going on there?
It's connected to the band gap. Okay. And that's as far as I can tell you. I mean, that's an observation.
Mm-hmm. Thank you.
So the small band gap have less bi-exitons, and the big band gaps have. The big band gaps have low bi-exciton quantum yield, and the small band gaps have high bi-exciton quantum yield.
Okay, I think we should go to our coffee break, and thank you very much to all of our speakers.
think it's time to get started. It's a real pleasure for me to introduce the next speaker in today's symposium, Professor Uri Banin. I've known Uri for a long time because we were both graduate students together in the very early days of ultra-fast spectroscopy when you had to build the lasers yourselves with your own two hands. And Uri got his PhD at the Hebrew University in Jerusalem with Sandy Ruman doing some gorgeous experiments studying the photodissociation of small molecules in solution and understanding fundamental aspects of how molecules come apart and how the energy is distributed. He then decided he wanted to change fields, and so he moved to Berkeley and did his postdoc with our honoree today, Paul Alvisados, where he learned about the synthesis and the characterization of semiconducting nanocrystals and other particles. After his postdoc, Hebrew University decided they absolutely had to have him back, and so he went back there as a professor, and now he currently holds the Alfred and Erica Larish Memorial Chair in the chemistry department. Uri's research there has kind of dominated the field of nanocrystals of all types, from synthesis to single particle and rod studies to a wide variety of applications, including things with semiconductors, mixed semiconductors and metals, and just all types of particles that you can imagine. I think we're going to hear all about a whole bunch of different types of particles today. He took some of the expertise in this field and started a company called Q-Lite that was eventually successfully sold to the Merck Corporation, I just learned. And there's just lots of applications for the things that Uri has done. In addition to all of his prowess with nanocrystals, Uri has also done lots of service to the community. He's an associate editor for the Nano Letters journal that Paul also started, so again, lots of connections here. And so Uri has been one of the founders of the field altogether. So it's a real pleasure to introduce Uri Banin.
Thank you very much. Okay. Thank you very much, Ben. And congratulations, Paul, for this well-deserved award. And indeed, you continue to serve as an inspiration to me in the excellent science that you continue to carry out and the joy of science, and also in leadership positions. So Nano Letters, founding this important journal in our field, and also basically transforming how papers will be handled and published way back 20 years ago already. And also in being able to be such a leader in general in science, assuming so many important positions. So I thought it would be very fitting today at the Seaborg Symposium to talk about artificial atoms, inspired by the giant who discovered 10 atoms, 10 real atoms, and how we make from artificial atoms artificial molecules. So really, the colloidal quantum material field has evolved tremendously from wonderful size-controlled quantum dots, which we've heard about, into shape control. And shape control is really an area which Paul pioneered for the field in this paper, making nanorods that really enrich the selection of colloidal quantum materials that we can make today. So we can ask questions about dimensionality, one-dimensional nanorods, two-dimensional platelets, mixed dimensionality such as nanodumbbells, seeded rods, and so on. And of course, this comes along with the ability to control properties, emission, which is such a useful property for so many things, ranging from displays to bioimaging and so on. And really, let's think about these as artificial atoms. And the artificial atom character is something that I was working on early on when I joined the Hebrew University. We worked on indium arsenide quantum dots. This is something that I started off during my postdoc with Paul, where indeed, as Dimitri mentioned, already at that early time, Paul identified the importance of going to all these other elements in the periodic table and trying to make 3-5 semiconductors, even though their chemistry is really much more difficult to carry out in solution. And in this case, it was indium arsenide quantum dots, which I learned to synthesize in Paul's lab, and also started studying the spectroscopy of these systems. And they were quite ideal when coming back to Jerusalem, because they have a narrow gap, to apply to them another method which really will show you the artificial atom character very vividly, using scanning tunneling microscopy and spectroscopy with my colleague, Professor Oded Milo, in physics. And what we did is we placed these nanoparticles on a gold substrate. We can image them, and then park the tip on top of the dot at low temperature, at cryogenic temperatures, and carry out an IV curve which clearly shows the band gap region here of suppressed current. And then you see that the current at both the positive and negative bias sides increases in a step-like manner. Each step is basically opening of a channel for further single electrons to actually occupy a new state in the quantum dot or charge up an existing state. So when we look at the DIDV of this spectrum, which is proportional to the density of states, we can really see the band gap, and we can see the artificial atom character. The onset of current on the positive bias side shows a doublet. This is the S-like state. You can put 2 electrons in this conduction band S state. And this separation between them is the charging, single electron charging energy in this small quantum dot. Then we move up in bias, and the next peaks appear when we hit up the P state, and indeed you see a 6-fold degenerate P-like state in this spherical quantum dot. The valence band in these systems is always complicated because of the valence band mixing effects, but still you could identify 2 groups of peaks, 2 groups of multiplets related to 2 levels at the edge of the valence band of these indium arsenic quantum dots. And when you carry out the size effect of this, you can really see the artificial atoms have advantages, so to speak, that we can control the properties by changing size through quantum confinement. The band gap will open up. Always we see the S state with the 2-fold degenerate character at the onset of the conduction band, a larger separation, a higher order multiplet of the P state. The charging energy increases as you go to smaller size. The S to P barrier gap also increases because of confinement. And then we have 2 groups of peaks also here, which relate to the 2 levels in the valence band. So these are the artificial atoms. And how can we enrich this huge selection of such well-controlled colloidal quantum materials is really by trying to think about nanocrystal chemistry. So I'll tell you today about quantum dot dimers, which would be the simplest form of a colloidal quantum dot molecule, and some analogy to what we can do when we take 2 hydrogen atoms and make the H2 molecule with hybridization of states, looking for bonding and antibonding states and coupling between 2 quantum dots in this artificial molecule. And artificial molecules have been looked at with the physics community using molecular beam epitaxy. And these are grown within gallium arsenide using strain, Stransky-Krastanov type growth mode of quantum dots. So these are disc-shaped quantum dots typically. The second dot will nucleate where the strain field is actually enhanced on top of the first dot. So you do have an opportunity to look at coupling. The coupling scale, the energy scales are typically quite small. It's operational only in cryogenic temperatures. Typically, we're talking about millivolt and even sub-millivolt levels for these kind of quantum dots. And this is something that colloidal quantum dots may be better in because we can go to room temperature, larger scales, smaller sizes, closer dots together, stronger coupling. And of course, at the end of the day, we also have the opportunity of having a freestanding quantum dot molecule, which we could manipulate to do both measurements and later perhaps applications in different scenarios, bioimaging or being in a display and so on. And this idea of making colloidal nanocrystal molecules is again something that Paul was a pioneer of. And this is in geometrical control. So these are papers from the time that I was actually also a postdoc with Paul that, together with Peter Schultz, they took DNA strands and started to make gold molecules, gold and metal type molecules using the DNA to organize the molecules in very fancy manners. This is very good for plasmonics type response where you can have hybridization effects of the plasmonic emission. Even in semiconductor quantum dots, there is this paper from Paul's group in using actually organic linkers to make dimers of quantum dots. However, in the quantum dots case, we really are limited by having the DNA connections or having organic linkers, because at that point the barriers are too high, so coupling energies would be negligible. And so our approach to this, interested in coupling, serendipity helped us here when we looked at coupled nanorods. We had 2 nanorods. These are zinc selenide nanorods. which actually grew in a very peculiar shape, forming rod couples. It's a very interesting architecture and different in some properties compared to nanorods. But actually, the separation between the two rod arms here is dictated by the presence of the organic ligands, oleolamine in this case. So still, the coupling between the rod arms would be very small, as these are large barriers. Going into dumbbell architectures is another possibility, taking the two active apices of the nanorods. In this case, it's zinc selenide with zinc telluride, so again, a cadmium-free system. And it's a type 2 system, so electrons would tend to localize in the zinc telluride region and holes in the zinc selenide. And however, the issue is that, again, for coupling, we still have a large distance here. And so even though these were first possibilities for coupling, we were looking for something else, and our idea was now to fuse two core shell nanocrystal structures in a manner which could be generalized, and then use the shell basically as a barrier which we could tune by tuning the shell thickness and the fusion reaction conditions. And indeed, these core shell quantum dot artificial atoms are highly developed in the field. So of course, if we want a display, we will choose the type 1 band alignment, in which case electrons and holes are well protected. You can get very high fluorescence quantum yields, but you have other opportunities. You can generate a type 2 band alignment to separate electron and hole between core and shell architectures. You can generate something in between, and these are the type of artificial atom core shells that I will talk about in my example today, which has cadselenide cadsulfide, where the barrier for the electron is rather low, and therefore it's kind of delocalized over the entire dot, where the hole is still localized, what we call quasi-type 2. But in any event, these are tunable and robust artificial atoms for what we want to do. And we're going to actually be able to, in principle, tune the barrier, because we can tune the shell thickness. We can tune this neck, also the width of the neck, by the fusion reaction conditions. We can eventually, I'll talk about homodimers, but we could think about changing core sizes, having a different core, so we have a heterodimer in mind as well. We can go into type 2 band alignment as well. And at the end, we'll have this kind of particle, which is really like our typical colloidal nanocrystal in terms of the control of surface and manipulation and so on, being freestanding. So I'll talk about the synthesis strategy, some characterization of the structure, the quantum coupling that we calculate and how it compares to our experimental measurements, and some coupling mechanisms that we can reveal with single dot spectroscopy methods. And the fabrication really uses a template silica particle, a few hundred nanometers in diameter, to which we bind the first quantum dot. And then we use a masking layer of silica to actually fixate that first layer of quantum dots and also passivate the surface against further binding of quantum dots. We then use a linker molecule and add the second dot, forming a dimer on the surface of the silica. In the next step, we etch the silica away, left with dimers, which are unfused. And now we go into a fusion reaction. This is actually a new step. Some of this was used in metal particles and so on. But now we go into this fusion reaction to actually form this coupled dot system, and we purify that so that we have a nice population of dimers at the end. So let me show you how this looks in experiment. But before that, just an introduction to the building blocks. We choose to look at cadselenide cadsulfide, which is well controlled. And you see that we have small quantum dots with small cores and rather thin shells. These are expected to, let's say, show stronger couplings, and larger core shell particles, which may show a little less coupling, but are perhaps easier to characterize in detail of structure and so on. And indeed, to this end, we want to know our artificial atoms, because that's how we're going to actually construct the molecule. So these are wurtzite shaped particles using aberration-corrected electron microscopy installed 2 years ago at our nano center now. We can really analyze and image very carefully the structure with the facets and relevant architecture that would actually lead later to the formation of the coupled molecule. And now let's look at the different stages. We have the silica particles here. You see decorated with the first quantum dot. We then use the masking, so now you see that the silica becomes a bit corrugated. We still see the quantum dots on top of this sphere. In the next step, we bring in the linker. We use a tetra linker to have a stronger link here. And then adding the secondary quantum dot, you see that on the surface of the silica, we do generate these kind of dimers. Then etch away the silica. We're left with unfused dimers for one after purification of the different dimers. And then we go into this fusion step. And you see these are fused particles that this is demonstrated for the larger core, 1.9 radii core, 4 nanometer thick shells, and the smaller ones, which works nicely. And yeah.
How do you avoid getting larger multipliers?
So the reason is that really it's a stepwise manner. So now we have this particles that are actually fixated on the surface. Yes, they may have more linkers, but we can control the number of linkers. And then there's a steric hindrance, so you don't get a lot of higher order oligomers by this method. It's something that we can quite nicely control. At the end, we also purify by size-selective precipitation, where we get rid of monomers and so on. So again, the fusion is a step that we really had to look into carefully. And there is a nice window to work at, but at low temperature, 120 degrees centigrade, for example, it's not enough to actually fuse and get the atoms going. At high temperature, 270 degrees C, there are ripening effects, so we actually compromise the dimer and they may collapse. But in between, we have quite a nice window between 180 and about 240 degrees centigrade, at which case we do have fusion and without significant ripening, as we can suppress that by having excess zinc precursor added as well during this process. So there's a nice window to work with for the fusion reaction. Now let's look at the characterization. So really, after fusion, we do have a continuous lattice formation, coherent lattice formation between the two quantum dots. You can see that indeed the EDX analysis shows very nicely the preservation of the core shell architecture. We can identify the cadselenide cores with a selenium map, and also in this cross-section you see the two cores nicely situated within this dimer. Yes?
Why is there no grain boundary?
So there is actually, it depends on the actual attachment. Okay, so here our bonds are formed through fusing two lattice planes, and it's actually constrained because it's not like an oriented attachment process where we completely freely let two particles merge along a well-defined plane. So it really depends, the specific lattice formation across this interface will really depend on this initial step of actual binding between the two particles initially created with the linkers. So we have some homonymous plane attachment possibilities. So there's a range of possibilities here. There's a homonymous plane attachments. In this example, the 101 to 101 facet or 100 to 100 facets are actually linked. So we can actually analyze each of these dots in terms of the zone axis, so to identify really which planes are being attached. So some cases are homonymous plane attachments. This is one example. Other cases will be heteronymous, in which case we have two different planes actually fuse, forming another type of neck between the two particles. And we've done that kind of analysis for quite a few particles. So this is kind of statistics. Between homo and heteroplane attachments, it's about 50-50%. Now we can go to what we know about reactivity of the different faces of the Wurtzite lattice, which has led to this discovery of Paul about shape control. The reactivity of the 002 faces is quite high, especially the 0001 knot facet, which is characterized by a terminal cadmium atoms with 3 dangling bonds, which is highly reactive. And that would be the rod growth axis in the Wurtzite nanorods. And so those are actually quite dominant in both homonymous as well as heteronymous plane attachments. Another abundant connection that we see is for the 100 planes here, which are more ubiquitous. They're less reactive, but more ubiquitous. And the 101 facets are much less participating in this game, probably because of steric hindrance in terms of being able to actually link and attach and so on. So this is what we see in terms of structural analysis. We can do this also in the small quantum dot molecules. We can tune the fusion reaction to somewhat lower temperature. You can see again both examples of homonymous and heteronymous plane attachments. And you can clearly see that we maintain the core shell architecture here as well. In the line map nicely, you see that selenium from the core is correlated with less sulfur in the thinner shell that we have now when we go across with the EDX line scan here, or cross section. Okay, so we have these particles now, and we can now start to ask about do we or do we not, and what type of coupling can we see? So first of all, just looking at fluorescence of the small core shell case of the molecules, we saw a redshift. This is about 13 millivolt redshift and significant broadening. In the large core shell architectures, we see no shift and a very small broadening. So yes, we do assign this to coupling, to quantum coupling. It is much larger than typically the MBE quantum dot pairs, okay, which are on the order of 1 millivolt. Of course, it's much smaller than hydrogen, than in a hydrogen molecule. And still, we can observe this at room temperature. We also see changes in the absorption. Similarly, we have a redshift here. And here we have also a comparison with the unfused dimer. So if we overlap the band gap transition, you see that in the case of the unfused dimer, they overlap perfectly almost with the monomers. But upon fusion, there is the redshift, and there is also broadening, and the excited state broadened, also all indicative of coupling effects. When we actually look at the absolute absorption cross-sections, we see that the band gap absorption cross-section is somewhat lower in the fused dimer case. In the unfused dimer, it's just a double that of the monomer per particle, is what you would expect, because you have now 2 particles per dimer. And at higher energies, that's also the case for the unfused ones, but perhaps the broadening and some effects of the coupling actually reduce the relative oscillator strength for the fused dimer. So those are evidences for some quantum coupling, but to better understand the quantum coupling, we go into some calculations. What we're going to do is take 2 core shell quantum dots, couple them together, and just like in the hydrogen molecule, they'll hybridize, forming bonding and antibonding states. We want to calculate these hybridization energies. And to do that, we're using a solution on a grid using COMSOL, where we will solve the Schrödinger equation. We will add also the Coulomb interaction in a second step when we want to compare to optical experiments in an iterative manner. And so solving this, the energy scales of interest are the hybridization energies for these 2 bonding and antibonding states for the electron. Because this is cadmium selenide, cadmium sulfide, the electron has a much lighter effective mass. Also, the band offset between the cad selenide and cad sulfide in the conduction band is rather small. So hybridization will be much more significant for the electron and actually quite negligible for the hole. So initially, I want to just tell you about what hybridization energies we see for the electron states. And what we can do is look at dimensions, different dimensions. So we have this model of 2 core shells. We look on this axis at the barrier thickness, which we can in principle tune by changing shell thickness, and also the core diameter that we can tune by changing the size of the quantum dots we start with. And another parameter that we can examine is the effect of the band offsets, which is a number that is somewhat in dispute or still even in discussion in the literature for this system in colloidal quantum dot core shell of this type. Starting with 0.1 electron volts, we see in general the trend that you would expect that as you go to small cores, small barriers, these hybridization energies increase. They're on the order of 20 or so millivolts. If we go to 0 band offsets, again, you see this trend very clearly. Interestingly, there is some different behavior a little bit here when we have a 0.3 volt EV band offset in the calculation. There is a region where there is a large splitting. And so just let's look at this a little bit more carefully. In this region where we have rather larger cores and thicker shells, the trend is clear. We start from quite small hybridization energies that increase when we have lower band offsets. This case is almost like having a larger elliptical particle with a ground state without nodes, and then the second state, which is the antibonding state, having one node in the middle for this flat case of zero band offset. Interestingly, when we go to this point, there is a flip. So the hybridization energy actually increases for the larger band offset case. And this is related to this quasi-type 2 nature, because now the lower state is actually localized within the two cores, and the antibonding state becomes somewhat delocalized. So we have this opposite trend, which wasn't so expected, that we will actually get larger hybridization in this case. So this is one effect that we look at, the dimensions. The other one is, that I want to share with you is the effect of the constriction, the neck width. So that has a big effect as well. That's somehow also comparing what happens in unfused dimers, because there the neck is, even though they can touch and so on, because the ligands are short, you know, and they can still somehow interact. The neck has a strong effect on these hybridization energies. In small neck widths, the hybridization is very small. This is for 0.1 EV band offset. This is for 0.3. When we actually increase the neck width in the simulation, you see we can increase the hybridization energy quite significantly, reaching, again, about 20 millivolts for this particular model calculation. Okay, the next step is now, if we want to compare to experiments, to also add the Coulomb interaction into the game. So if we look at the hole, it will localize the electron because of this Coulomb attraction. That's also true for cores. In the core shell case, in the dimer case, this is true for monomers, and in the dimer case, actually the hole hardly hybridizes because it's, as I mentioned, heavier and it has a larger band offset. So it will localize in one of the cores and lead also to significant change in the bonding and antibonding states that we will see. So already in the cores, you see that this will stabilize by the Coulomb interaction, the ground state, or this transition of the electron state, the electron-hole transition, leading to a redshift. And this will also change the nature of the bonding and antibonding state. So the first state, the lower state, will be more localized within the first core, but it still delocalizes away. And the second state is actually more on the other side. And then this will allow us to now define the redshift, which is the fusion energy, what we call, related to the hybridization and further shift here, minus the difference in Coulomb interactions between monomers and dimers. And the other opportunity that we can do now is also to calculate overlap integrals, which are proportional to the absorption cross-section. And so with this picture in mind, this is another calculation where we now change the core diameter in this architecture. And what I won't go into all the details. I think I will not have enough time for that. But in general, we see both for 0.1 and 0.3 EV of band offsets. In general, there is always a negative shift, a negative net shift in this case between the monomer and the dimer, taking into account both hybridization as well as Coulomb interaction. And specifically, looking back at the experimental points that we had for larger and smaller core shell dimers, you see that there is very good correlation between these kind of calculations for these specific systems. So the large core shell quantum dot shows no redshift between the monomer and dimer, both in the calculation, including the Coulomb interactions, and also in our experiments. When we go to the smaller core shell systems, that's when we start to have redshift, which correlates nicely between experiment and theory. And also these absorption cross-section questions and changes may be addressed to some extent with this type of modeling. Now we can go ahead and ask further questions concerning coupling beyond just these redshifts and broadening effects related to hybridization and so on. And another change that we see quite significantly when we make the dimers is significant shortening and quenching of lifetime. And it's much more significant when we compare the small core shell dimers relative to the larger core shell dimers. So there's a quenching already in the unfused case, but that is significantly more enhanced when we fuse, and especially so in the small core shell dimers. So we're going to use, to this end, some single dot spectroscopy techniques. This was well introduced by Munji, looking at single particles on a camera or with the APD setups, looking at blinking effects where the off state is related to the formation, for example, of a charged particle, which then has quite fast Auger recombination, which leads to non-radiative decay, and looking at this kind of off state. Then we can also do lifetime measurements on single particle with time-correlated single photon counting, and we can do also photon correlation, looking at bunching, anti-bunching, and using what Munji had taught us about bi-exciton to exciton quantum yields and so on. And first of all, looking at the lifetimes, you can see that indeed what we saw in the ensemble is also reproduced for single particles statistically. These are the distribution of monomer lifetimes, which are nearly single exponential in this case, and they're actually significantly shortened already in the unfused dimer, but even more so when we go to the fused dimer. In the larger dot core shell dot system, there is also quenching. It's not as significant, and note that the unfused to fused case hardly show a change in terms of the quenching effect. So in terms of understanding the different mechanisms, we can think about two coupling mechanisms. The first one would be energy transfer. It's not exactly homodimer energy transfer because they're really somewhat different. There would be one which may be a little bit bigger than the other, and therefore could serve as an acceptor in this type of scheme. That would be active also in the unfused dimer. It's, of course, strongly distance dependent, but the distance between the two cores is perhaps not so different between fused and unfused dimer cases. So we do have energy transfer also in the case where we have just the unfused dimer. However, upon fusion, we see further quenching related really to a tunneling mechanism, we believe, and that is indeed much more significant in the case of the small core shell compared to these larger core shells, which have much less this type of quantum coupling taking place. So these are the different coupling mechanisms which can actually occur already in this homodimer case. And another type of study is to look at the blinking. So the single monomer shows the very classical type of behavior of an on-off, well-defined states related again to this off state being an incident where we have charging and then the trion, for example, being formed such that it's now experiencing very fast non-radiative Auger recombination. And so it turns off, and then it would deneutralize and turn on again. In the case of the dimers, we see a much more distributed level of photon emissions. You see, in general, we do get more photons. Okay, in general, we have a tail here to higher photon rates at the same excitation intensity. It is a dimer that could absorb more. But you see that the flickering behavior, not really a very well-defined off state, is seen. And that would be consistent with having slower Auger recombination. Imagine what we could have here is a trion, for example, where the electron could be localized on the other core. And this state could already be emissive because of this volume effect. Even here, so we don't see that. We see really this flickering behavior. But no, not yet. This is really kind of relatively young data, so not yet. But it's really something that is more reminiscent of what is seen in core with giant shell type of quantum dots. And indeed, you can actually do a time tag, time resolved decay, where you see the on state here is quite nicely nearly single exponential, and there's a very fast off state for the monomer. But in the dimer, it's much less distinct. It's even the kind of on photons, so to speak, are fast decaying and not single exponential. Then looking at the photon statistics, the monomer shows quite a nice contrast between the zero time, a nice anti-bunching contrast here between zero time, this is a pulse experiment, and the next pulse sequences. if we use what Munji has taught us about using this for a ratio of quantum yield of the biexciton to the quantum yield of the exciton, this really indicates the non-emissive biexciton of this type of core shell quantum dot. But when we go to the dimer, we have a significant lowering of this anti-bunching contrast. You see the level here. And we think that this could be a combination of both increase in potentially a biexciton, which would be actually situated with one exciton on each core, such that it could become emissive. So this factor would increase. And on the other hand, we do have quenching of the exciton quantum yield due to these two mechanisms that I mentioned of FRET and tunneling. And there could also be the case of charged trion states which contribute here to this reduction in the anti-bunching. And to this end, we looked at power dependencies. So in the monomer case, indeed, it's very difficult to actually change, I would say, the decays and see emissive multi-excitons in this experiment. But when we have the dimer case, we can, with increasing the average number of photons, move into this case where we see faster decay components emerging related to different multi-exciton states appearing in the dimer quantum dots. So to summarize that, we see that we have actually multi-carrier configurations, which are quite rich now. We have the possibility to have biexcitons situated on two different cores. They would have actually larger potential to be actually emissive because it's a much slowed down Auger rate. We have a different type of trion presence as well. And that leads to a very rich landscape of possible multi-carrier configurations here with reduced anti-bunching contrast associated with that as well. So to summarize, I've really talked about the synthesis strategy where we can generate these coupled quantum dot homodimers, and we can generalize this method. I've shown you the characterization, which shows the ability to achieve both homo and heteroplane attachments in this system. We have hybridization. The scale of hybridization for the cat-selenide sulfide system is 10 to 30 millivolts. It's sustainable at room temperature. We see broadening, we see modified absorption, we see redshifts on this scale, which we can reproduce by the simulations. And you've seen how important is the shell thickness. The neck thickness is very important as well in terms of controlling the hybridization energies. And we have, through single dot spectroscopy, suggested that we have tunneling decay routes that can reduce lifetime in the dimers, as well as a rich configuration of multi-carriers where both biexcitons and trions can still be emissive in this system. And what we've been looking at more recently is now to look at a system which will have perhaps a better defined architecture for the fusion. And to that end, particles which are of zinc blend, which are less studied, even in cat-selenide sulfide, but are developed. The zinc blend particles are interesting, of course, because they have the pyramidal 1-1-1 planes. It's more clean. And these are core shell cat-selenide sulfide zinc blend particles. Now, on the when we bind them, actually, you see that they preferentially take up this spike ball architecture, probably because they're kind of more bonding sites that actually adhere them to the surface of the silica. And then in the next step, what we see is that we actually get preferential tip-to-tip fusion rather than plane-to-plane fusion. So we form these bow tie architectures, and this is still preliminary work in terms of the structural analysis. We see what we get is like this really nice fusion of the apexes, and have not yet looked in depth about coupling mechanisms. But this is perhaps even a cleaner system, potentially at least, although it does tend to form the fusion through the apex rather than the planes. And looking further into other opportunities is that we can really use this Lego-type construction to generate also, for example, heterodimers. Just could be two-color two different colored dots with different sizes. And in general, this works. You can get the dimers released, purified, and you see that we have here a heterodimer formed after fusion as well. So now, really, the vision is, I hope that this can set the stage for this nanocrystal chemistry with coupling, where if we're thinking about the 150th anniversary of the periodic table being this year, out of 118 elements, 10 of which this great scientist discovered, we have 150 million organic and inorganic substances. It's still developing, right? It's not stopping. And just now thinking of the coupled quantum dots or the colloidal quantum dots as kind of artificial atom which generates our own periodic table, just thinking about 2,6 combinations, we can have type 1, maybe with 2 colors. We can have the quasi-type 2 is what we looked at for now, but you can have 2 different cores. You can have type 2 architectures as well. So there's a lot of things to do to unravel both the fundamental properties of single excitations, hybridizations, charge separations, multi-exciton states. And I think this can also lead to various applications, taking into advantage already what we know to do with just quantum dots in many fields. And so at the end, I'd like to thank my group. This is from the last year's Hanukkah party, along with all the kids and so on, and specifically Dr. Jabin Tzui, a postdoc working on the synthesis and all the characterization, Yossi, my student, doing a lot of the calculations of spectroscopy together with Dr. Somnat Kolei, another postdoc, my lab manager, Merav, Nir, and Doa. I want to thank the people at the Nano Center and collaborators, Eran Rabbani, as well as Professor Oded Milo. Funding for this is mostly from the ERC and the project which is called Coupled NC. And at the end, again, congratulations, Paul. This is an atomic reconstruction. And happy birthday. This is calculated. So.
Did Sarah pick that color?
Oh, yeah. I know that was not coordinated, but yeah.
So, Uri, the bi-exciton, the 0.7, what are statistics? That would be really interesting to repeat one of these experiments on 2 photons coming out of this couple.
Yeah.
Can you get entanglement directly from such?
You think not? I'm not sure, no. Yeah. So these are the usual quantum dots with our lifetimes and so on.
Maybe you can repeat the comment for people in the back.
So the question was if we can do the type of photon statistics analysis that Munji showed for the perovskite nanocrystals, and it's probably less possible because of the long T1 lifetimes that are typical for these. You saw the lifetimes. It's 5, 10, 20, 30 nanoseconds typical for these type of core shells. But perhaps maybe in other colloidal systems we have to see, because we do have an opportunity to do this for other materials. So let's see. Yeah, just think.
I'll just talk loudly. What is the coupling mechanism that you think you have? So there's transition dipole moment coupling. There's charge transfer type coupling. There's exchange type coupling. Do you have a sense of which part is dominant here? Or?
Okay, so initially, first of all, we calculate the hybridization energies. You saw the scale. So definitely for the shifts, the spectral shifts are related to hybridization combined with a Coulomb interaction at the end. But that's the reason for the shifts, because I think we have a nice comparison between unfused case and fused case. So the shift and broadening are really related to hybridization. Now, in terms of lifetime quenching, already in unfused dimers, we see quite significant quenching, even before fusion, which to me is suggestive of energy transfer, although there could be a little bit of tunneling because they're colliding, and could be a little bit of tunneling. And in this type of kind of what we would call homofret, so I mean in aggregates of quantum dots you will often have some redshift as well, but you'll have also shortening of lifetime associated with these processes. But I think this is a great model system because we can vary the shell thickness now systematically and look at distance effects and so on. And so I think we'll be able to address the exact mechanism better when we do those type of experiments, even in greater depth. So we have in mind a combination of these two, energy transfer as well as tunneling effects associated with the quenching that we see. Yeah. Thank you.
This one? That one, okay. Well, it's my great pleasure and honor now to introduce Paul Vasados, or as he's generally known in our community, the other Paul. I think you can all read the long list of impressive awards he's won: the National Medal of Science from President Obama, the Von Hippel Prize of the Materials Research Society, earlier this year the Welsh Award, many ACS prizes. He's an elected member of the National Academy and won their Chemical Sciences Prize, American Philosophical Society, American Association of Arts and Sciences, and so forth. But there are really three things you should know about him that you might not be able to read off a CV. The first is the science, and you've heard a little bit about that already. We're going to hear it next from Paul himself. The second is that he's not afraid to roll up his sleeves and do the hard work to make things happen. As you heard, he's now the editor and founded Nanoletters. He's the executive vice chancellor and provost at Berkeley. Before that, he was the vice chancellor of research there. He was the director of the Lawrence Berkeley Laboratory. He established the molecular foundry there. He led and chaired the nanoscience panel for the Obama White House of Office of Science Technology Policy, where we proposed and roadmapped the BRAIN initiative. And he's really been a champion for our field. And the third thing is that it's never a straight path. And he's been great about talking to young faculty and would-be faculty. And I'd suggest if you're an assistant professor or thinking about being one, you talk to him about his path. If you're a journal editor or thinking about being one, talk to him about Nanoletters. He was also key to the establishment and suggested the establishment of ACS Nano, and one of our earliest and best advisors on how to overcome the barriers that we faced as we got started. And so to me, that's all the more impressive about where he is now and where he's going. So let me leave time for him to give the talk that we've all been waiting for. Please join me in welcoming Paul Vasados. I'll add that we haven't quite known each other for 2/3 of our lives, but more than half. And he just celebrated a big birthday. I think it was 29. Earlier this month, so we can work on that one at dinner.
That's it. All right, thank you so much, Paul. And what a pleasure and what an honor. Thank you so much. In 1981, I was a first-year graduate student at Berkeley, and I was a teaching assistant or graduate student instructor, and I was in the lab with the undergraduates, and they had to do something called qualitative analysis. They would get a little vial of a clear liquid, and in it were some combination of unknown ions, and their test was to discover through precipitation reactions what ions were present in the solution. So I'm nervous, of course, because this is a very stressful point for the students. They get tested on this, and they have to get, and I wasn't sure I knew how to do all of it myself, and so it was a moment of a lot of stuff going on, and I was helping a student, and then suddenly there's this big ruckus across the room, and there's this very large man who is doing a student's unknown in about like 15 seconds. He boom, 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 boom. He writes down the ions, and he goes to the next student, and everybody's like crowding around him saying, it was Glenn Seaborg. And the joy of science for him was so great that he would periodically just show up and start doing the labs with the students. And so that was something that I've always considered to be a wonder in a human being, that he was, with so many accomplishments, he still felt that joy of being involved. And he did so many other things besides science, so that's very inspiring. I'd also like to just thank all of the colleagues here today. I mean, what a, you mentioned Executive Vice Chancellor and Provost. I have to sneak out to go have a science break, and so you gave me the most amazing science break I could ever possibly imagine. I mean, what an astonishing set of presentations. So thank you, all of you who have presented before me. I will try my best today to give you a little bit of some of my perspectives, some historical, and some of our really current work. A month ago, I was at this, this event where there was a symposium, and then, another award was associated with it. And so the symposium was the whole day, and it was CRISPR-Cas9. And then, the award was, quantum dots. And and so here you go. You look at those and you say, well, okay. How can you not be in awe of biological matter, which has about the same size, but of course the complexity of what can be achieved by the biological system is just unreal. And I think for all of us who work in the nanoscience field, our building blocks are achieving higher and higher precision. Dimitri, you mentioned the example of polymers, and certainly many polymer chemists aspire to one day break out of averages, to have composition along the chain of their own control and so on. I think for us, some of the most interesting goals really do revolve around trying to get to atomic level control. I won't talk today about structure of single particles because there's just not enough time to do it, but I will say that I don't think it's out of the question that we could get to really high levels of precision in our materials, more than we have already. But we'll look at some of the questions around rigidity and around average control and other things like that. But for something like a CRISPR-Cas9, everything is really about health and biological systems for food, those kinds of things. For our materials, certainly there are really important health applications, but to my mind, there may be other ways of getting at that. But to me, perhaps the most important area of impact for nanoscience will actually be in the areas of energy. And these problems will, of course, intensify. And nanoscience itself, and I think Sarah's talk illustrated in a very nice way how rich it is. There are principles inside nanoscience, a very small number, but when architected properly, they provide ways in which really important contributions to the problem of the global carbon cycle are and will continue to emerge over time. So that motivates me very much. I think those are the two things. We'd like to achieve much higher level precision, and we'd also like to see these things have some impact in the world of energy. So I mentioned to you, there's a small number of really foundational concepts that underlie this field. There's not large numbers, and mostly they're scaling laws. And so we'll touch upon these three, which are ones that, at various times have occupied my interest, and also ones which kind of come back in funny ways. You study them at one point in time, and then at a later point in time, they get more currency. But there are many others for charging, for magnetization, for Auger scattering. There are, a beautiful list and a finite list of important scaling laws, which really describe what happens to matter when it becomes smaller and smaller. Crystals melt at lower temperatures. The effect of defects changes dramatically. We'll show that momentarily. And of course, there are all the quantum size effects. And these three can all conspire together to create a lot of opportunity for really interesting nanoscience. So this is a measurement of the reduction of the band gap of the melting temperature of CAD sulfide crystals. You can understand immediately why it happens, of course, which is as a crystal gets smaller and smaller, the number of bonds on the surface, the number of atoms at the surface becomes larger. They're not connected on the other side to anything else. You can also think about it from a classical point of view of the liquid having a lower surface energy than the solid. In any case, either way, you'll see this kind of 1 over radius approximately dependence of the melting temperature on the size. And the important thing is, Dimitri, you talked very eloquently about the problem of what temperature can you really grow the crystals at. And we'd like to grow crystals at, say, a third or something of a melting temperature. That's typically a good range to grow a crystal at. And so what's very important about it is that materials of technological interest, like semiconductors, when they're very small, they enter a temperature regime where if you are at about a third or so of the melting temperature, that's at the temperature where an organic liquid boils. And therefore, they become accessible to synthesis by that route. And Munji, played such a vital role in understanding this, along with Mike Steigerwald and Chris Murray and others. And so the method of injecting a precursor into a hot organic liquid is, it turns out, sufficient. It's a sufficient set of conditions for growing many important semiconductors as small crystallites. Now, it's true, it's tantalizingly on the edge of the temperature required for the 3-5 semiconductors, which has, if it had just been out of the question, it probably would have simplified our lives enormously. But it's just right on that edge. And so, we're always tempted to try. And I think your idea of trying to go to yet higher temperatures is right on. So we know all those things. And Sarah, since I did want to celebrate your amazing work, and so it is true that if we have one of these tiny crystals, there is a profound change in structural transformations. If we take a small crystal and pressurize it, it will go to a denser structure. If we release the pressure, it will come back. And what's remarkable, there is, of course, a size dependence to that, but what's much more remarkable are the giant kinetic effects. This phase transition has a hysteresis that's massive. That means it basically can be overpressurized and will not nucleate. And the reason that it won't nucleate is because the tiny crystals have been made at a modest temperature, but high enough that all the defects have been pushed out of them. And as a consequence, there's no place to nucleate inside the crystal. When it finally does nucleate, the modern simulations all show it always happens at the surface. But for a variety of reasons, the nucleation at the surface is actually a harder event to occur than the nucleation at, say, a grain boundary inside the crystal itself, or other kinds of defects in the crystal. And for that reason, these crystals essentially are, quote, single structural domains. And so that's a really interesting thing that happens in these, and that Sarah showed long ago. So if you combine all three of those, you can make tiny crystals, well, all three. We should say the quantum size effect. I think it's by no doubt familiar to everyone in this room, and Lewis did so much, as well as Munji and others, to help us understand it. But it's a very simple idea that in the semiconductor, the electron and hole have a quantum volume that is, can be larger than that of the crystal, so that as they get smaller, the kinetic energy of electron and hole increase. So does their Coulomb attraction, but nonetheless, you can see a very large shift in band gap as a function of the size. And my good friend here, Shimon Weiss, was a colleague at Berkeley years ago who was working with us during the earliest time and was really the innovative thinker around using these in biological imaging for the first biological imaging experiments around the same time as Shuming Ni. These are, of course, as a consequence, tiny crystals, high quality. They can absorb and emit light in very beautiful ways, are as a consequence used extensively now in quantum dot televisions, and that's because of their color purity. They have relatively narrow emission spectra compared to organic molecules, and the colors can be called out relatively precisely so that they produce really very high quality color displays. Not too long ago, I was in Hong Kong, and there was a sign there for quantum dot televisions. You can sort of see it. It's not a great shot, a little bit of a foggy day. this was, I'd say, a few years ago. But just a little bit away, you could see also the OLEDs right there. And so there's, in the TV business, there's a bit of a, OLED versus quantum dot TV thing going. But I still think you could bet on the quantum dots because it's certainly true that photostability and the colors at high brightness favor them today. But as Dimitri alluded to, it absolutely will happen that there will be full electrical injection into quantum dot arrays for televisions. The progress in that is dramatic at this moment. And when that occurs, then the black point will no longer be advantaged for the OLEDs. And I think the balance will tilt significantly for quantum dot-based TVs. Okay, so now I'm just going to follow up a little bit on the structural transformations. And Uri, you referred also very nicely to this period after the initial quantum dots were made when there was a sudden explosion in the diversity of quantum dot shape. In my own research group, actually, it's an interesting thing. For the early part of our career, of my career, and most of the people working in this field, when we would first make these tiny crystals, you had to wait to be able to go and image them. And so it was my fantasy to one day have an electron microscope in our own lab. And eventually, I somehow managed to pull that off. And once we had our own microscope, you could make a sample and then image it. And that cycle could be minutes, not, sometimes weeks. And it didn't take long. After that, within a year, we were making a whole pile of different shapes that we, previously could really never have made sense out of. So I think it illustrates how much nanoscience as a whole relies upon imaging of different kinds that allows us to see. One of you earlier, I can't remember who said that little crystals have existed for hundreds of years, probably thousands. We know that they're in various, they're in stained glasses. We know they were used in colors that were used by ancient civilizations. They've been around for a really long time. And they were certainly studied extensively in the early part of the 19th century. Ostwald and others studied these kinds of materials. But you couldn't really figure them out till you could see them with an electron microscope. That's my opinion anyway. And so for us, once we had an electron microscope, we could create this huge variation of different kinds of shapes. And that was a huge advance. And in fact, ultimately, these shapes follow mostly from a very small set of chemical transformation types. There are only a few. You can do branching, there's ion exchanges, and there are addition reactions which, depending on the relative diffusivities of a binary system, can lead to the creation of hollow structures. And there was a period of time when we were elaborating these and also found, not all shown here, that these things could be done independently from each other in sequences in different orders, in the sense meaning in the end that the nanocrystal as a chemical object can be manipulated in the same way that an organic molecule can be built up in stages. And you can perform make an initial building block and then add to it and then do another reaction and make its elaboration greater and greater. And this is in the early stages. I think, Uri, what you showed is a very beautiful example where the quantum effects of that are being observed. And I think it will be a theme for quite a while. Now, in Sarah's work, we saw that the nanocrystal could change its volume substantially and do that reversibly over and over again. And that's because it was a single structural domain without a defect inside. So you ask the question, well, what happens as crystals get larger and larger? At some point, they're going to have defects inside them. And what are signatures of that? And that's a question that has interested me for a very long time. And Asaf Ben Moshe has been studying separately when he was doing his PhD thesis at Tel Aviv University, was studying various effects of chiral ligands and chiral nanocrystals. And he has come to work with me for a couple of years now. And so I wanted to tell you a quick story about how the tellurium nanocrystal gets its shape. It's one of the famous stories in science. Pasteur himself saw, of course, left and right-handed crystals and sorted them. But he himself also noted a conundrum which is as yet not fully solved. You can have a material which has a local atomic symmetry that is chiral and make a non-chiral shaped crystal out of it when you crystallize it. You also can go the other way. You can have a material which is fully locally chiral, non-chiral, and will make a chiral shape. I mean, either of those can have. So it doesn't seem to be a clear link. And if you ask somebody, how will I know if I make a chiral-shaped crystal or not? Mostly they will say, you've got to try it and see. And that's because the mechanism by which something shows itself to have a chiral shape is not fully known. And the mechanism isn't fully known because you can't follow the thing all the way through. And so, of course, nanocrystal evolution has the potential to answer the question of what will or will not produce a chiral shape. And so these set of experiments, I think, kind of reveals one mechanism that is, I think, pretty unambiguous. If you have a crystal at very low supersaturation, it will, if you have a solution at low supersaturation, it will try to nucleate however it can. And it turns out that very low monomer addition can produce chiral shapes. I should say here, I neglected to mention, one of the things that Asaf has done is he's developed an automated way to take images of thousands of nanocrystals and be able to have it automatically detect, is it a left-handed or a right-handed one? And you need that in order to do the study that I'm showing here. So here's there are two kind of hypotheses that you could have. One could be you have to have chiral ligands present. And another one could be there's just some intrinsic mechanism by which the crystal forms a chiral shape. What you can see here is a case where we have grown in the presence of, what you can see here along this line is we grow crystals at different supersaturations. And regardless of whether there are ligands present or not, we can make crystals that in the case where we're growing crystals at a low supersaturation, we can see that whether we have left or right-handed ligands present, we will end up making both populations, but one is much smaller than the other, and physically and in number. So it changes both the nucleation and the growth rate, and we can invert that. But the most important thing is if we simply turn the growth rate up by having more supersaturation and getting more facile nucleation, then they will no longer be chiral. So at very low supersaturation, they will tend naturally to form a chiral shape, and that is almost certainly nucleated by a screw dislocation, but of course the relative amounts of those can be adjusted by having present in the solution a chiral ligand. We can show that there's an initial screw dislocation. What's so interesting about it is if there's a simple screw dislocation, then in one rotation around the crystal, you'll change by 1 atomic height. But in fact, that single screw dislocation can disassociate in the symmetry into 3 partials so that the net total energy of that is a lot lower. And that's in fact what happens in these tellurium nanocrystals. This is an example where we've gone from a single structural domain to one that's more complex as the size becomes larger. And I think there are many examples of that, and those are kind of outgrowths, really in some, those are the through lines, Sarah, from your thesis, are studies of phenomena like these, of when defects start to come into crystals, but they're very singular in nature and they can be tracked. They're not just random. Okay. There is, of course, a large diversity of nanoscience building blocks. We're talking just about crystals, but there are all these other beautiful components that are out there. They can be mixed and matched together. And as I said to you earlier, I think the biggest applications may be in energy. Some of the largest ones are in batteries. I've mentioned here, I've highlighted here the example of the volume change that Yi pointed out years ago, which are indeed an example of that, of the scaling laws that we discovered earlier. There are others, of course, in catalysis and so on. But these correspond, in my opinion, to amazing cases where scaling laws improve known energy technologies. This method of harvesting energy is known, and you make it better, okay? And that's all to the good. But I do think it's also true that underlying the fundamentals, there are profound changes that can occur when materials become very tiny that open up different ways of harvesting energy than those which are available to us when we harvest energy with large systems. And to some degree, that's the most interesting question, is are there examples like that? And I will try to show my opinion that there is one. Here are some examples of ones which might exist. There are many. There actually are many, where you might see phenomena that occur due to operating an energy conversion at a very small scale. There could be many examples of those that look completely different on small scales and very advantageous as a result. So that's something we would like to know. So here are three things we can say. Little things can be easier to make and more perfect than big ones. That's the exclusion of defects. That they can be made on the same length scale, and that the range of what is possible to make can be much larger on these very small scales. Now, going back to our beyond dream CRISPR-Cas9, this just shows from the McCammon group, the thing jiggling around. This is what it's like when it's actually, out there doing its business. Ours are, comparatively speaking, if you made a movie of its jiggling around, things wouldn't move almost at all in comparison. Everything's kind of locked down, right? So let's think about that. And the materials that Munji showed will also be part of the topic now. There's a grand debate in material science. There's the frozen school. The frozen school says every atom should be locked in place. And when you do that, that's what happens in your laptop. Every atom is locked in place. And if any atom gets knocked out of its normal place, then, the thing will no longer function. And then there's the flowing school, if you like. And in the flowing school, things bounce around a lot, like this one was, like the protein was. So the question becomes, which will be better in nanocrystals? They're so small, things can fluctuate a lot. Which will be better? And I'm going to test that in an example of an energy conversion system that I don't believe you can do with bulk materials. Okay? That's my opinion. We'll see if it's true. And that's the luminescent concentrator. So we know that if we want to compress a gas, we can do PV work. We can compress the gas. It can then expand. And we can make out of this a cycle that is an engine. What if we were to replace the gas, let's say it's an argon gas or nitrogen or something like that, what if we replace that with photons? Is it possible to do that? And that's what a luminescent concentrator is an archetype of. So in a luminescent concentrator, we have a slab of a material. It turns out it should be a quantum dot material, as you'll see in a moment. And it can absorb the photons which are allowed to come in. And so in can come red, green, or blue photons. Or, I'm sorry, in can come green or blue photons, but there's a special mirror here. This special mirror on top will perfectly reflect red photons, but perfectly transmit green and blue ones. Okay, that's the condition. And then this is just a complete perfect mirror here. So photons are coming in. The quantum dots absorb them, and then the light just bounces around. And if the quantum yield of the quantum dot is very high, then a photon will never be lost, and you'll just keep packing photons inside there. And that's the equivalent of the compression cycle of a compressor. then of course you can decompress it, and in the decompression, if you make a cycle of those, you can make an engine with photons. It's in principle possible to do this. Okay. It turns out to be kind of difficult. And there's a very simple reason why. Yeah, there's a very simple reason why it's difficult, and that's because when you load up a quantum dot into a polymer film, as the quantum yield gets higher, you can harvest more and more of them, because when the green and blue photons come in, they excite repeatedly. The dot can absorb and re-emit several times. And if at any point you lose one of those photons, it's like a gas compressor that when you compress it, some of the gas escapes from the compressor. So if the quantum yield is low, then you will lose your photons. Now, it turns out the quantum dots are also very good, because the way they do this is by taking, imagine, for example, that you had red light, and then it's scattered in all directions. And you know, of course, you could never take scattered light and put it all back into the laser. In this system, what you're doing is taking blue light and converting it to red, and it's that energy difference which is used to compress the photons and make them all go in one direction. So you're putting your PV energy work of compression here is being done by changing the energy of the photons from blue to red. And so if you have a good Stokes shift, you can compress the photons. If the quantum yield is good, you could achieve really good factors for the concentration factor. So a standard cadselenide cadsulfide quantum dot can do this quite well, because the shell will absorb, the core will emit. There is a very large effective Stokes shift, and it can also have a very high quantum yield, as we'll see momentarily. This could make a refrigerator. So for example, if you have a laser sitting here below the band gap and there's a vibration in the quantum dot film, when the laser comes in, if the system is hot and there happens to be a vibration, it can catch that photon and then emit it with a very high quantum yield, and you will have eliminated the phonon from the system, and as a consequence, you'll have moved towards making a refrigerator. So if we look at the quantum dots, we can see two roads to getting to them, one with thick walls and the other with the perovskite quantum dots that Munji was just talking about. And this will be an example of a frozen quantum dot, and this will be an example of what I will call a flowing quantum dot. And this will be the last thing I'll show. So if we have one of these systems here, indeed I showed you already, it absorbs light in the shell. It emits from the core. There's a very nice gap between them. These are the spectra of real samples, and they're working just fine. And now the question is, we want this quantum yield to be somewhere up here, let's say around this region. To get to a decent refrigerator, you've got to be sort of in that range somewhere. And so these systems, how could we measure their quantum yield? It turns out conventional methods for measuring them are not so good. We measure it by measuring the heat that's output. Basically, if we put in, and this was a very nice collaboration with Alberto Soleo. David Hanifi was the student doing that, who's now in a postdoc with my group. And so we can take photons of different energy, excite the quantum dots, and as the energy approaches the band gap, if the quantum yield is exactly 1 at the band edge, then there will be no heat at all when you bring the system down to that level. So by measuring the heat, we can find whether the quantum yield is exactly 1 or not. And it turns out that, for example, in this system, the best one we can make, it's around this number of 0.996. So it's not quite good enough yet, actually. It's off by a little bit. But this is the frozen system, and you saw earlier all the, how much people have studied it. Here's this other system. It's the one that Maxim Kovalenko showed a little while ago, and which Munji showed. And here's one thing that you can say about them. You can have this kind of cesium-lead halide system with the beautiful photophysics, with the allowed optical transition that Munji showed. And if you just simply put chloride ions in, they will substitute for the bromides at room temperature. The system emits the entire time. It's very bright the whole way through. you can go from bromide to iodide. The point is, given that you can do this exchange at room temperature, turns out these bromines are also moving around all over the place at room temperature inside that crystal. Nobody is sitting put. The atoms are all moving around. And so this is an example of a nanocrystal that's truly fluxional. If you pay a little bit of attention to the surface of this nanocrystal, you can make it have what appears to be very close to a unity quantum yield. It hasn't been measured by the photothermal technique, but it's very efficient. What attention is that you have to give to the surface? Well, I mentioned to you that those halide ions can bounce around and move around inside here. And it turns out that what can happen is at any given moment, there can be a missing halide ion. One can actually, they're loosely bound inside there, and one can pop off the crystal surface. In fact, that does happen. In a typical sample that would be made, say, with the Kovalenko method, probably about 20% of the halide ions on the surface are missing. They're just not there. And that's what provides the emptiness that allows everything else to kind of move in and move out and do it so facile and get such quick exchange. So if this is present, then it turns out that it does indeed make an electronic energy level that is a weak trap. It's not a very strong trap, but it's a weak trap. So either you can push more halide ions on there, or you can put something else on there that blocks that site and takes it out of the gap. And either one of those strategies could possibly work, but it's just important to remember this is a very fluxional structure. When we go through and measure with some care, what we find is, as I said, there may be about 90 bromine vacancies for a typical, sample. If you take a lot of care and you eliminate them, then you can find out how much each vacancy contributed to the non-radiative rate. And it turns out that one bromine vacancy would reduce the quantum yield in this system to 0.995. So this very fluxional system is good, but it has limitations. And it's about as good as the best frozen one we've ever made. The only problem is, I can't say this for sure, but my opinion is that you can't do a whole lot better than this, because if you bind more strongly onto those halide sites, you pull the crystal apart. So you've got a real conundrum here. A fluxional system, it's hard because there's an equilibrium defect rate in the fluxional system. Whereas in the system of cadselenide, you go up a little bit in temperature, and now at room temperature, all the atoms can be effectively locked in place, and you can make a system that's quite good. If the temperature of the system goes up a little bit higher, a la the 3,5 gallium arsenide that Dimitri showed, then this method of making them isn't good enough anymore because you can't anneal out the defects in the first place. So what we find is if you lower that temperature of the cohesive energy of the crystal too much, you end up in a fluxional regime. It's fascinating how good it is. It self-heals. It does many amazing things. But in the end, you will have an equilibrium concentration of defects present that I don't think you can easily eliminate. So in the end, if you wanted to make a photon refrigerator or any number of other photon-related energy technologies that are like the ones I was describing, I think you'll do better with frozen than you will with fluid. That's my opinion. And I think I'm going to wrap it there. There's another little section I could show, but I'm worried that I'm going to just go. Okay. So this question came up a few times today of can we take one of these dots and couple them well together or not? And a huge amount of beautiful work. Wenji, you worked on this years ago. You have worked on it, Dimitri. Uri, it was implicit in the work that you were talking about. This is a really hard problem. So here's the thing. It's just as annoying as all get out that this perovskite quantum dot has no walls, nothing's protecting excitons, nothing's going on, but nonetheless they have absolutely spectacular mobilities, they work beautifully, and it turns out for a solar cell, the equilibrium density of electronic defects just isn't very important. I mean, for the application I showed you with light emission, it matters enormously, but for many it doesn't. So the question is, can we make a frozen system that will keep up with the, or let me put this another way. For the optical case I just showed you, where we're harvesting photons, the frozen system definitely beats out the fluxional one. But so far, when we're building with nanoscale building blocks, the fluid one has beaten out the frozen one because the equilibrium density of defects is low enough. So the question is, can we bring these together? Now, if we have ligands in between the crystals, and we referred earlier to the energy variations that come from crystals not being identical, that's sort of shown here by the colors. I think it's really hard to get good transport in a system like this. There are studies of it, but it's very hard to do. The one case that I've been involved in at least was with Jambo Gao a few years ago, where he showed that if you optically pump one of these quantum dots, even when there are very thick ligands that are completely saturated, huge tunnel barriers, if you put 4 or more excitons inside one of these dots, multi-electron phenomena will periodically promote a dot through scattering, and then it can tunnel, because it's at such a high energy, it can tunnel through these very thick, very large distances. And so for about, let's say, 500 picoseconds, you can get a heck of a beautiful transport in there. That's pure. I think it's really not any kind of hopping, variable range. It's just a really nice system. But that's when you're pumping it like crazy, so it's not that interesting. So the question becomes, can you take one of these things and couple them together? And Uri, you showed a very nice example. This is what Justin Andri is doing, and the reason I wanted to show this was because Justin is an alum from this august university. He was working with Sarah, and he's come to do his PhD, which he's now completing with me, and he's just an amazingly brilliant person, so thank you. He's really tall, like Glenn Seaborg, and who knows, maybe he'll be like Glenn Seaborg. He certainly smiles beautifully, and he's a wonderful man, and he's taught me so much. So here, we can take these crystals, and this is Justin's idea. He will orient attach them, and he claims, lock them down on a substrate. They'll all be aligned, so they won't have the funny alignment effects, and then he'll grow material in between there, and by growing it in between effectively, he wants, of course, to make the mini bands. So here are some crystals. They're large ones. He has 2 different crystal facets that he can terminate them with different faces. He can join them and make them join together in different ways. And long story short, when they grow together, sometimes they'll come together oriented very nicely, and all the little defects will kind of go out the edges, and they'll be just fine. They're very nice crystals. Sometimes when he puts them together pairwise, they're tilted. There's a step edge. When they tilt, then you end up with some defects inside. And Justin has done very careful work where he's measured the temperature and time dependence for these defects to anneal out and go out to the surface. He's done it for like all different kinds of cases. It's really very thorough work. It's published recently in ACS Nano. These are the examples of the kinds of things that he can now regularly observe, where there are many crystals all attaching to each other, and these are now just plain old crystals. There's no core inside. That's published work. So now he's taking core shells. These are the very, very high quantum yield samples. They're really extremely luminescent. And he takes these. So before these things are attached to each other, this little core here does not feel any defects that would make it non-radiative. There may be some there, but it doesn't feel them enough to cause it to not be able to emit light. But now you take them and you do a couple of ligand exchanges to get them closer together. There's a volume change when you do that. It might make them tilt a little bit. So this is the correlation of the density of the dots. And what you see, and you can see that it goes all the way out to maybe, I don't know, 24 dots or something. So they're really well aligned with respect to each other for a very large distance. And then when you remove the ligands, it drops off a little bit. And then when you start doing the scylar stuff, it drops off a little bit more. So at the end, I guess they're ordered by about 7, 8 dots locally, where they're kind of really very highly aligned with each other and translationally predictive and so on. If you do it on the core shell dots, you can see this is now the STEM EDS, and you can see that the selenium is indeed in a kind of an array. And if you look at that, again, you can see that it extends out so that the positional order is quite high. Unfortunately, if you do the spectroscopy on this, what you find is that it's a system that's dominated by the defects that take place at this newly grown interface here. And so we have not yet found how to make a system that will really talk to each other electronically well and be a complete array. In that sense, Uri's choice of simply doing a dimer is clearly a better choice for the time being, because you don't have to get all the surfaces to work at the same time. And Justin knew that when he picked the array, but he doesn't care. He wanted to do the array, and more power to him. Go, Justin. So I'm going to just remind you of these three fundamental things I hope you do remember from the presentation. Little things can actually be made higher quality and even more easily than large ones, which is a surprising thing, but it comes because of the reduction in the melting temperature and because of the fundamental rule about pushing defects out to the edges, which really drives a lot of the nanoscience that will be related to energy harvesting. It is true that nature builds functionality, and the first true functionality typically arises on the nanoscale when there's enough complexity of components to make them really interesting. And I think we're starting to see a lot of that too. When we try to make solid state materials, we're finding that when we build them out of nanoscale building blocks, that's a really good scale to build things out of, because it's versatile and because many things can work in your favor when you do that, like the scaling laws. And this debate will never be settled. It will be an eternal debate. But at the moment, the frozen school, I think, still mostly wins if you really want high performance. But what's shocking is, I would say, I'm not aware of an example from 10 years ago where I would have thought there was any material that could be fluctuating with a high degree of disorder in it that could perform as well as what those perovskites have done. They're just fascinating. And I think it's got to do with aspects of what their ionicity is, and there are a lot of really interesting things that come together in that. Maybe there are further ideas inside that will lead to us eventually having such a thing as near equilibrium electronic materials, near equilibrium, so that they're not locked like the laptop is, but things are kind of moving around inside, and yet they're still high performance. To me, that's an astonishing thing that could even be possible. Okay, so these are the folks from the high quantum yield quantum dot team that helped do the material that I showed you on the 0.996 quantum yield. The luminescent concentrator work has been a long set of collaborations, about 10 years of work we've been doing together with Ralph Nuzzo and Alberto and with Harry Atwater. Carissa, who's here on your faculty, was doing work related to the cavities of these when she was in my research group, so her picture is here. And Asaf did the work I showed very briefly about tellurium, and he's doing all kinds of things with chiral nanocrystals that I think is just really fascinating, so I'm learning from him. And Justin did the work I showed you on quantum dot attachment. And this is my current research group. They're just absolutely wonderful. And it is true that I did have a birthday recently, and I was so lucky. I thought at the end of a long day that I would be going to yet one more board meeting as provost at Berkeley. And I walked into a room, and there were about 250, this is a little bit later, some people had left, about over 200, maybe almost 250 of my coworkers over the years were there. It's a wonderful moment, and really made me feel great. And thank you.
Time for questions and comments. Justin.
It's just very tempting to start thinking about concepts of entropy when you think about these things.
Sure.
So you have photons coming in from all directions, and now they're being directed in a specific direction.
Yes.
So there's some
instead of doing PV work in this system, it's energy work. You're converting the photons, and then you're changing their entropy.
Right.
And it's that change in entropy that you're harvesting in order to make refrigeration.
So how do I think of what's the minimum energy difference I need between your absorption and emission to achieve like to actually get this direction?
So at 300 millivolts, you can do really well. If the energy gap is about 300 millivolts, there's enough energy there that you can do some very serious concentrating. Let me put it a different way. At a gap of 300 millivolts, it's possible to concentrate photons. I believe it's 10 times more than any geometric optic could ever do. Remember, in a geometric optic, the photons don't change energy. And therefore, there is a fundamental limit to how much you can change the entropy with a geometric optic. And the outperformance will be very clear at a few hundred millivolts of gap, which these materials have. The problem with the concentrators we make now actually is not, they are not limited anymore by the quantum dots. They're limited by the quality of the mirrors. Making a mirror for that will reflect the red light but transmit the green and blue and do it at all angles and with enough nines on that is actually not that easy to do. It's clearly achievable, but in our work, it's not been as good as what is done with the quantum dots. But in principle, it is possible. And if you paired, let's say, which is, I think, theoretically quite possible, a 6 nines mirror set with a possibly possible 6 nines quantum dot set, you could make a really great refrigerator or really great, you could do a lot of energy things with that. And I didn't have time to really say this, but the real advantage of it is that the place where the, in all of these photon refrigerator type devices, where the cooling, because it's photons that are doing the business, there's no mass connection. So where you're cooling and where your source of photons are can be completely different, like the sun and the earth. But you could, you can, this is also the basis for ways you might do propulsion. There are many things that you can do, many energy conversions that you could do.
There's some way to capture the leaked photons and
put them back in? I don't know. I don't know. That's an interesting idea, but I'm not sure. I think they should first help make some cavities that don't leak. It's achievable, or at least ones that don't leak, as much as the ones we have right now do. So, yeah. I'll lay it on the problems on them. Yeah.
Okay, so this is a really exciting idea, which is not something I'd seen before. So what kind of efficiencies are possible with these hypothetical many nines that you're imagining?
Oh, they can be quite, I mean, they're like regular, it's like saying what's the efficiency of a combustion engine. It can be really high. I mean, they can do, it just all depends on how you.
Well, okay, but everything's limited. I mean, Carnot efficiencies are a limit. What are the?
Yeah, they have the same kinds of limits. I mean, there's not,
Is there a Carnot equivalent, and is it?
Yeah, I mean, for example, in the solar case, it's the difference in temperatures between the black body that's generating the photons and what the temperature of the solar cell is at that provides your Carnot temperatures. It's the same thing. So, how about, put it this way, the a luminescent concentrator coupled to a solar cell would have the exact same performance as just a plain old solar cell that directly harvests the photons. So it doesn't make a difference in the final efficiency. It's just you're using photons rather than gases. I hope that's, but that can be, there are circumstances where that really matters. I mean, the classic example, one of the colleagues here was studying the Starshot. A classic example of this is that you leave the fuel, you want to propel an object in space to go really fast. So you use photons to make a light sail. And so the fuel stays on Earth, but the massless photon sends the energy and it propels the object and makes it go. And And if you look at the that would be an example. If you look at the calculations of that, people have shown in the Starshot project that you can make a light sail in principle if you had good reflectivities and blah, 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 and you didn't blow the thing up, and so on, that you can accelerate an object to 1/4 of the speed of light and send something to another star system. So, I mean, there are things you can do with photons that you can't do with ordinary mass objects. And those are where this idea would have its purchase in cases where you just don't want to have
physical connection.
Right.
I was really kind of impressed by your phase transition experiments, old studies, rock salt, zinc, wurtzite. Ceresis. So, and because of these histories, is it possible to stabilize these metastable phases like rock salt?
Yeah, people have. We did that some years after because the surface energy. So, when you make the transformation from wurtzite to rock salt, you produce a shape of the rock salt that's an unhappy shape because it's topotactic, and there's no way to get from here to there. Let's say you make a crystal, and it acquires the shape that is the low energy shape for one condition, and now you force it to a new crystal structure. But it's by a single nucleation pathway that takes place at the surface, and that nucleation front just moves across the crystal, that it will now make a shape that's unfavorable. But if you have something that can bind to that unfavorable surface and stabilize it, then you can hold on to that. And we showed an example of doing that with the rock salt phase maybe 10 years after Sarah was there. So yes, you can, in principle, make that hysteresis big enough that something stays locked in place indefinitely.
Thank you.
So you mentioned the Florence School, right? The best example is the silicon-based transistor technology, right? So that's essentially Moore's law. And right now we're in maybe 7 nanometer mass production, a few years 5, 3. So what do you think what's the fundamental limit there?
To being able to use the silicon technology?
Yeah, right.
There's so many aspects to that question. That's a complicated one, and I think when people were working at 50 nanometers, they thought there was no way you could do 25, and then they thought there was no way you could do 20, and then they thought there was no way you could do 14. And as you pointed out, there are some feature sizes way down at 7 now. But obviously, at some point, you reach all kinds of limits that, at a minimum, in the silicon system, what really makes it work is the oxide on the surface, and there's a finite thickness to that. And what's great about the silicon system is that the oxide pulls all the levels out of the gap, but doesn't keep going all the way through the crystal. But it does go through a finite, it does have a finite width there, so at some point you hit that if you're trying to use exactly that technology. I'm not sure that's, how do I say it? I think the things we're talking about here with these systems, where they're built from the bottom up like that, and you make tiny crystals, and then you do things with them, I doubt that they're going to really be competitors to this kind of lithographic technology. They're going to make other things that are really interesting but different. That's my sense of it. Yeah.
Well, let's thank Paul and all the speakers for don't worry yet. I'm turning things back over to Rick Taylor for closing remarks.
So I would just like to thank all of you for coming far and wide. During the break, I met some of our colleagues from Cal State Northridge and from UC Santa Barbara, and they brought lots of students, which is really good to see. I want to thank our sponsors, which include the CNSI for providing a great site, ACS Nano, Paul, thank you, Nano Letters, Paul, thank you, Amgen. And I would especially like to thank Paul for a really, really inspiring talk and all the speakers. Thank you.